Well, good morning, and thank you all for coming. I really appreciate you taking the time to be here today. So first, as Professor said, I'm Thomas Kelly, and today I'll be talking about my Trident research dealing with polarization and variance of vector vortex beams in underwater optical turbulence. But first, I'd be remiss if I did not thank and acknowledge my wonderful advisors, Professor Abramov-Zamorovic, Dr. Nelson, Dr. Nee Warner, and my external collaborators, Dr. Fairlick and Dr. Forbes, who've all been instrumental in this project's success and giving me that little nudge to get some work done every now and then, and really got me to this point today. So this is my project, and hopefully after these next 20 or so minutes, it'll make a little bit more sense. So I'm going to go into what is a vector vortex beam, what is the degree of polarization, why you should care about both of these things, how we make these beams, and how they can be used to communicate information, and whether or not yes. So so we're here because the military and the Navy and scientific communities need to be able to transmit data quickly, reliably, and in very harsh environments, namely underwater. And wired communications are not always practical, so we need to find new ways of being able to transmit data. And that's the crux of this research, is how are these beams affected by the turbulence, and can we use that information carried on these beams to then transmit data? So the point of this research is to evaluate how the degree of polarization is affected by optical turbulence. We will evaluate that by looking at the degree of polarization variance with time, the statistical stability of the mean degree of polarization, and then the communication system viability. So optical turbulence can be found in our everyday lives. On a really hot Maryland day, you'll see heat radiating up off of the pavement and see the mirage effect and distortions in the light. That is a form of optical turbulence. And optical turbulence is formed by there being temperature gradients in the medium that we're looking through. And those temperature gradients leads to index of refraction changes, which then distorts the phase of the light. And those phase distortions lead to intensity degradation, as well as physically altering the beam, and it completely destroys and distorts how that beam looks. Because of that distortion, the data is lost in our intensity form, and we are attempting to evaluate how the degree of polarization of this light is affected by this turbulence. So a vector vortex beam is a special kind of laser beam that has a spatially varying polarization structure. So the characteristic part of this beam is that it has a helical twist applied to the light and also has a varying polarization structure that occurs at every point along the beam. So what this means is there's a unique state of polarization at every point around the beam spatially, and because of that helical twist, we then have a spatially varying structure. We look here on the right side of the screen, and there's a little graphic of what a vector vortex beam looks like, and at every point around the wavefront, we see there's a unique state of polarization, which is the characteristic nature of a vector vortex beam. So to make this vector vortex beam, we first start with two independent laser beams. We have one that's vertically polarized with a clockwise twist, and then we have one that's horizontally polarized with a counterclockwise twist. When we combine and overlap both of those beams, a property called non-separability occurs. And this property is where the beam's shape, that twist, and the polarization become intrinsically linked and intertwined. So what this means is that we cannot describe the shape without also describing the polarization. And the theory behind this is that when we distort the beam through our turbulence, that it affects both properties equally. It affects the spatial state of the beam as well as the polarization at the same time and at the same rate. And the theory behind this is that if we think about it as having a vertical and a polarization and a horizontal polarization, that relative angle between the two at this point is 90 degrees. And if we distort the beam, and in this case we're just rotating it, if we distort it and so it out looks like that red dotted line, the relative angle between the two branches of polarization are still the same. And because that angle is the same, in theory, our degree of polarization should also be the same. So this is the fundamental property that allows our vector vortex beams to be considered invariant, and throughout this project we'll be evaluating whether or not this hypothesis is true. So polarization is the process and act of aligning the photons of light and restricting them to oscillate in one direction. And we can characterize this polarization by using a thing called Stokes parameters. S0 gives us the total intensity of the light, S1 gives us the linear polarization, S2 gives us the diagonal polarization, and S3 gives us the circular polarization. And with these four Stokes parameters, these four metrics, we can fully describe the polarization states of the laser beam. Now we take those Stokes parameters, and then we put them into this nice equation at the bottom right-hand side of the screen to be able to physically quantify that value of polarization and make it a nice number. This degree of polarization quantifies the global state of polarization and is again, the main topic and subject that we are researching in this project. Experimentally, we can get this degree of polarization value by using a Thorlabs Curelux polarization camera, and that camera can detect all four Stokes parameters, and then in post-processing with MATLAB, we are then able to take those Stokes parameters, use this equation, and then give us a single value of the degree of polarization. It's important to note that if we have just a horizontally polarized beam, it's a normal laser beam, the degree of polarization would be 1. And once we start incorporating that vertical component, once we start getting that spatially varying structure that's inherent to a vector vortex beam, the degree of polarization becomes less than 1. This matters because for our communication alphabet, that limits the values to be between 0 and 1. So not a very wide range of values there, but that's what we are working with. So to make these beams, we first start with the helium-neon laser source, and then we propagate it through a beam expander. We then put these beams onto a spatial light modulator, which imposes a dual hologram, which then makes both of our beams. It not only makes the two beams, but then it also applies those helical twists and applies the orbital angular momentum that gives those beams that characteristic twist. We then put this through a linear polarizer, which then locks into the polarization to be vertically polarized. Because we need one beam to be vertically polarized, that beam just simply goes off the mirror and into the beam combiner, and no more work is done. But the other beam goes through a series of mirrors and a half wave plate, which then rotates that vertical polarization to horizontally polarized. So then we have both of our beams, both the vertical polarization as well as the horizontal polarization. And then we combine those two together, and then after a lot of painstaking alignment and making sure they're perfectly in the right direction, we then get our vector vortex beam, which then we propagate through our Rayleigh-Bernard turbulence emulator, which then distorts the light and allows us to evaluate how it will perform in these harsh environments. Here's our benchtop experimental setup, and jokingly, this was version 26 up here because it felt like every other week we were ripping it all down and putting it back together. It really was an engineering feat or a challenge to get these beams to be perfectly aligned and to be superimposed. Every time that a beam hits a mirror or something that's not constant in between the two paths, sends them off in random directions, and they really do not want to come back together and be aligned for the entire propagation path after we've combined them. So it definitely was an art form to kind of figure out how to get this done, but we figured out how to use these mirrors in conjunction with the spatial light modulator to get these beams to be perfectly aligned, superimposed, and then have our characteristic vector vortex beam. So Rayleigh-Bernard turbulence in our turbulence emulator works by having a hot plate on the bottom of the water tank and a cold plate on the top of the water tank. That hot water will rise and the cold water will fall, and that leads to turbulent eddies in the middle of our turbulence tank. Those turbulent eddies have a thermal gradient by nature, and that thermal gradient leads to index of refraction changes. And those index of refraction changes cause the light to become distorted and degrade our beam. We chose Rayleigh-Bernard turbulence because Rayleigh-Bernard, by nature, is controlled, replicable, and a random process. So this basically means that from experiment to experiment, from trial to trial, we can replicate the turbulence again and again, and we know what to expect, and we know what is happening inside of this tank. And with the foundational work done by Professor and some of the previous research students, we have proven that our Rayleigh-Bernard turbulence tank is a stochastic process, validating these claims. So the next step is how do we detect the beam? And as you mentioned, the turbulence tank really does do a good number of destroying and degrading these beams. And part of that is beam wander. What this means is that basically the beam will dance along the screen and physically move where it's centered at. This poses a problem because our camera is only so big and the beam is a certain size. So if the beam moves too much, it's no longer on the camera and we cannot dynamically move that. So to combat that issue, we either get a bigger camera or we make the beam smaller. And unfortunately, we couldn't get a bigger camera, so we made the beam smaller. So we used a beam minimizer to make the beam smaller, and then we put that onto the polarization camera. However, the CureLux camera can only detect S0, S1, and S2. It cannot detect S3, the circular polarization. So to account for that, we take half of our beam, split it off, and put it through a quarter wave plate. This quarter wave plate translates our circular polarization states into being linearly polarized, and then we do a dual detection setup where we're actually detecting both of those beams on the camera at once, and that allows us to get the full range of Stokes parameters, allowing us to calculate the full degree of polarization. So now we get into the fun stuff, our experiment execution. So the first phase was making sure that we could actually make these beams, that we could detect these beams, and that the vector vortex beam actually existed. After this, we had to evaluate whether or not we could modulate the DOP, whether or not the degree of polarization was stable in a non-turbulent environment, and make sure that all of these things work together nicely. After this, we were able to move on to turbulence testing, so we propagated these beams through weak and moderate turbulence. And after a lot of data processing, data wrangling, and some nice MATLAB code, we were able to analyze this data and see how exactly our vector vortex beams were affected by our optical turbulence. So the first thing we had to prove was that we actually had a vertically polarized beam and a horizontally polarized beam. That's what this image shows. We showed that we did indeed lock in the vertical polarization states, and then we also showed that the half wave plate was properly aligned and oriented to give us a horizontally polarized beam of light. Next, we had to make sure that we were actually generating a vector vortex beam. So if we look here at the left, we show our 4 Stokes parameters. So S0 shows a very nice donut-shaped intensity profile, which is what we expect, and shows that the beams are aligned, at least visually. And then as we look at our linear polarization, we don't see much. And that's exactly what we want, because the vertical and horizontal polarization are canceling each other out in that linear domain. And then in S2 and S3, we actually see this very nice interference pattern. Well, this might not look much to you all. This is actually exactly matching the theory of how these beams will interact. And this proved and validated that we actually did make the vector vortex beam, and that we had this spatially varying polarization structure across the wavefront. After this, we used our detection setup, used that MATLAB processing code, and was able to demonstrate that our degree of polarization was inherently stable over time in a non-turbulent environment. All of this testing was done at 11 frames per second, and in this case, this was taken in air. So this allows us to move on to the next phase of our research, because now we have proven that we can generate these beams, that we can detect these beams, and that all of the post-processing code and whatnot is working properly. So the next step was to see, could we actually modulate our degree of polarization and make a viable communication alphabet? So we used a thing called a neutral density filter, which adjusts the intensity of the light. And through adjusting the intensity of the vertical polarization state, this allows us to modulate our degree of polarization. And seen here on the right side of the screen, we have 5 different levels of degrees of polarization, and each degree of polarization can be thought of as a unique letter in our communication alphabet. So it's validated that yes, we can make a communication alphabet because we inherently have unique DOP states, so we have unique letters to be able to communicate and transmit data. And we also demonstrated that the degree of polarization is invariant in a non-turbulent state, even as we modulate and change our degree of polarization. So after we make these beams and validated that, we now have to look at our turbulence strength and see how is the beam being affected in the intensity, as well as being affected of our scintillation spatial distribution. So if we look at the left on the intensity profiles of each beam, we see that in the top left, we have a very nice characteristic vector vortex beam with a very nice donut shape. However, as we increased our turbulence and we moved down to the bottom right-hand corner of the screen, the beam got a little bit distorted. The beam began to lose its characteristic donut shape, and at certain points, you can barely even tell that is a vector vortex beam. This is inherently showing how much the beam is being degraded by our optical turbulence, and showing how much the beam is wandering around our camera aperture. On the right side of the screen, we have our scintillation spatial distribution. And scintillation is basically a measure of how much the intensity is changing and fluctuating. So if you look at like the night sky and looking at a star, that star twinkling is due to scintillation. And that's still the effect that's seen here, is the intensity fluctuation in the light. So in our top left, with no turbulence, we have a very nice vector vortex beam with no big yellow peaks, so basically that's showing that there's no scintillation occurring. However, as we move farther to the right and farther down, we see massive yellow spikes. We see massive scintillation occurring. And this basically is validating and showing that our turbulence is in fact altering the intensity. And as we increase the turbulence, as we increase the temperature gradients between the two plates, the beams are becoming more and more distorted, which matches the intuition of that. So as I mentioned earlier, the beam wandering was a massive engineering struggle and a massive hurdle to deal with. So because of it, those index of refraction changes, they almost act like prisms in the water. And those prisms, as we know maybe from our Physics 2 class, definitely distort the light and cause it to bend and move around and wander. So as you see, in no turbulence, the beam stays very centered and does not move much around the camera aperture. But then as we increase our turbulence states, the beam likes to walk a lot. And we actually saw almost a 400% increase from our no turbulence state to our turbulence state. And the beam went over and touched all four corners, all four sides of our camera aperture, which is definitely a struggle with detecting these beams, because we need to have all of the light go into the camera aperture. So it'd be very helpful in future research to either have the beam become even smaller and learn if we can do that, or have a larger camera aperture and figure out how we can do that. But unfortunately, it's a pretty challenging problem, as there's not many cameras that are bigger than this, so that would go into a whole rabbit hole of research, but that's how these things kind of work in the end. And so here is our main research and research summary. So as I said earlier, we are trying to evaluate how is this degree of polarization affected by our turbulence, and how is it affected over time. So first, I want to draw your attention to these three bolded lines, the darkest ones, the dark green, dark red, and dark blue. Each color signifies a different level of degree of polarization, so a different value. So with our no turbulence states, we see that those lines are actually quite steady, showcasing that our beams are invariant across about 100 seconds and do not change very much in this non-turbulence environment. On the right side of the screen, you will see a probability density function, which shows how much of the degree of polarization is occurring under that curve. So on the dark blue on the left, it's a very pointed needle. This basically is saying that most of our values lie in that needle, and that there is not much variation in the data. As that curve broadens and widens, we are seeing more variability in our values and more changes in the values, showing that the beam is less invariant, showing that it is variant. So as we increase our turbulence to the weak turbulence state, we start to see the signal becomes very noisy. We start seeing more fluctuations between the three states, and then we also see our probability density function start to widen, showcasing that the variance is increasing and that the beam is in fact being affected by our turbulent state. As we further move to our moderate turbulence, that signal-to-noise ratio is increasing and becoming more and more of a challenge. And we see that there as our PDFs become extremely broad and start to overlap. That's basically saying that the beams are becoming more variant, and at every spot where they are overlapping, we cannot distinguish between the two levels, making it extremely challenging to use this as a communication alphabet. Between our no turbulence states and our moderate turbulence states, we saw the variance increase by 2,000%, which is quite substantial. But what's interesting is that the mean degree of polarization, so the average value across time, only changed 10% between the no turbulence and strong turbulence. So the conclusion that we can make from this is that yes, our optical turbulence does introduce noise into the system and does cause our degree of polarization to become varied. However, the mean value does not change. So even though the light is becoming distorted, that value is still carried through the turbulence, but we are just having trouble always detecting it. If we saw that the value was being inherently distorted by the turbulence, we would not have that mean degree of polarization carry through the entirety of the trial. So now we're looking at our detection confidence. So how likely is this to actually be used as a communication system? And the way that we determined that was we came up with a value called our detection probability. And the way this worked was that we took our mean degree of polarization value at the non-turbulent state and said, okay, that value, let's say for instance, is 0.5. And now we're going to say if any value falls in between plus or minus 5% of that mean value at the weak turbulent and moderate turbulent states, then we would be able to detect that beam. When we applied that threshold to that plus or minus 5% to our degrees of polarization, we found that as we increased the turbulence, it became less and less likely that we would actually be able to detect this beam. What's interesting to note, though, is that our ND filter not applied, so our base degree of polarization, actually experienced much higher probability of detection, less variance, and we hypothesized that that is because the intensity of the beam is higher because we are not attenuating that signal, and we think that maybe that is why the probability of detection is higher and there is less variance. It would be very interesting in further studies to further dive into why that is taking place and if that can be further improved by increasing our beam's intensity at its source. So clearly, a plus or minus 5% threshold would not work in this instance. So we moved to see, okay, how can we make this system actually viable? And to make it actually viable, we have set our threshold plus or minus 15%. And what that means is that we could only have about 3 to 4 letters maximum in our communication alphabet because we can only work with 0 to 1. So we could have a DOP at maybe 0.3, 0.6, and 0.9, or some variation thereof. But what we found was that even as we increased the turbulence, we were still able to detect that state, and this, in a very unique case, does show that we could use it for communication alphabets. However, it is probably not the best use of this system. So to conclude, in ideal conditions, the degree of polarization is invariant and could be utilized to communicate and transmit data. However, as we increase our turbulent state, our vector vortex beam is affected by the optical turbulence, seen in our intensity degradation, our beam walking, and also we see that as the degree of polarization increases, our variance of the signal also increases. This research proved that vector vortex beams have limited usage for communication and are significantly affected by optical turbulence. But because the beams are affected by optical turbulence, and we have this spatially varying polarization structure, we have those 4 Stokes parameters that are all independently affected by our turbulence. So future research could take those values that we know are changing and then use that to be able to characterize the turbulence. So the next, research question that someone could go into is how can we utilize this for environmental sensing, which is the other side of laser beam work. Overall, these past 2 years have been extremely formative and sometimes fun experience. And I am extremely grateful for everyone's support and for being here today. I think that we've been able to have some extremely interesting and novel results that hopefully I presented today. And without further, if there's any questions, I would love to take those at this time. Yes, that's quite a loaded question, Professor. Um, so currently there are very limited use cases of where ships are using optical communication to go from in the water on like a submarine or a UV, propagating out of the water into the air and to a drone. That'd be a very difficult case. But even underwater, that's still very difficult. So this experiment evaluated the baseline metrics, just looking at turbulence, and the ocean environment is much more complicated, much longer vision distance, and this is the first step in that process. Currently, I don't think that there are any viable communication systems that use optical communication in an underwater environment that are actually in practice in the ocean. This only looks at the turbulence that's experienced in the underwater environment, but then there's also the biological matter, salinity, and all the other variables that become into the system. Does that answer the question? Oh, yes, absolutely. And that's why we're doing this research, is that we think that there are a better solution to sonar, a better solution to the radio waves. And this is the first step in that process to getting us to be in a position to use optical communication in that challenging underwater environment.
Great job, Thomas. Going back to your benchtop setup, you had unlimited funding.
Whew, that's a good one. So I think what will be really cool is that right now, to change and modulate our degree of polarization, we have to use a physical ND filter. But I think that out there's a way to have a variable ND filter and be able to kind of program into that, being able to change that ND filter and then basically attenuate it. So for this to actually be a viable system to communicate, we have to be able to quickly modulate that frequency and quickly change it. So I think being able to introduce that would be really cool. And then also we can always have better mirrors, better equipment, and if we can have a more pure vector vortex beam state, we may have a less variant beam. And if we have a more pure state, it may be affected less by the turbulence, which then could further reinforce that this may be a more viable system than we first thought. Mm-hmm. Good question, Professor. So in this case, we chose really Bernard turbulence because there is an experimental foundation that is the turbulence that we can accurately replicate and show that it's a true stochastic process and not a chaotic process. So that's why we chose Rayleigh Bernard. And as we shift to a more complicated, more dynamic environment as seen in the ocean, that may completely change how this project is done. But I think the underlying point of this is that turbulence is still those index of refraction changes, and those index of refraction changes will still be occurring even if the turbulence is not Rayleigh Bernard turbulence. So I think that this research would probably be able to be transitioned into a different form of turbulence that's not Rayleigh Bernard turbulence. But that would obviously require more experimental testing and to a change of our setup. But I don't think that I can make any conclusions one way or the other without doing further testing, sir. Great question. Thank you for that. I believe that if we did increase our intensity of the beam, it would not affect the beam wander. The beam would still wander and dance around. We actually had a carpet of images that showed all 9 beam wander plots at all the different attenuation levels and all different turbulence levels. And we saw that at each attenuation level, it was consistent across the board, and the driving factor there was actually the turbulence, not the attenuation. Thank you, sir.
All right, now beep that.
That's the plan. Thank you, man. Appreciate it. Thank you, man. Appreciate it. Thank you so much. Oh, yes.
Okay,
green
this
light.
is what I have. Thank you.
Thanks.
Oh, look who came. No, I'll be fine. I'll be fine. Thanks. Thanks for coming. Thanks for coming. I will. I will. Thanks for coming. What? Is that what you're talking about? No. Look that way. No, it's not. It's really hot. Yeah.
It gets warm in front of that screen.
Yeah, I tested it out last night. And I was like, oh, geez.
Feels
It's hot.
It feels a little cool in here, but I think with the lower screen, it's probably better for you guys.
Yeah, thanks for setting everything up. This is chemistry, so you'll understand. You'll understand this. Some of these it's hard to understand because I'm like I don't know like what people are
You
doing.
learned it,
But
right?
hi, nice to see you. I'll give you a hug. I'll give you a hug. Nice to see you. Thanks for coming. Sorry, I stepped on your shoe. Yeah. Hi, Kate.
Okay, we're going to start in a few seconds if you want to speak.
Yeah, it works.
Okay, we're going to continue with our next speaker. One of her advisors is going to do the introduction.
Hey, good morning, everybody. I'm Professor Joey Latta, and it has been my absolute pleasure this last year and a half or so working on research with Midshipman Cicero. So Margot has done internships in support of this research, and it was great working on her with that, on all of her other travels, which there are a lot of overseas travels in the past few years, as well as advising her and working with her in the classroom. I have been just intensely impressed with Margot's confidence, her drive, her curiosity throughout this whole process, and I think all three of those show like how interdisciplinary this research is. I mean, she's a nuclear engineering student. She probably spent most of her time in the chemistry lab in this, but she was wearing lab coat, goggles and gloves in the chemistry lab constantly. And then she would transition over to the nucleonics lab to do her kind of nuclear science and engineering portion of the research. And then she would transfer to the additive manufacturing lab and do kind of the materials and mechanical engineering aspect of the research. So just a truly interdisciplinary project. I've been very impressed, and it has been a lot of fun working with her for the past few years. With that, Margot, please share.
Great. Thank you. Good morning, everyone. I will be presenting on additive manufacturing of photopolymerizable lithium-6 organic, almost done, plastic scintillators. So for the primary objective, I want to build a radiation detector that can detect gammas, fast neutrons, and thermoneutrons. The identification and discrimination of all three of these is called triple discrimination. The radiation detector that I'll be building for this is called a plastic scintillator. Now, I will be addressing two issues with current plastic scintillators. The first one is that plastic scintillators historically can only detect one or two of these types of radiation. The second is that these plastic scintillators are made in bulk, so it takes a lot of time, it's very expensive, and there's a lot of limits to geometry. To address the first issue, I'll be using a Naval formulation, and to address the second, I will be 3D printing it in an SLA off-the-shelf Formlabs printer. So, for some background, special nuclear material is used to make nuclear weapons, and it can be transported in various quantities. This special nuclear material gives off neutrons among other radiation. And these neutrons are hard to detect because A, they give off no charge, and B, they are shielded. When you shield neutrons, they slow down and they turn into thermal neutrons. So, in order to detect special nuclear material, again, that's made in nuclear weapons, we need to have a detector that can detect thermal neutrons, fast neutrons, and gammas. So, the way a scintillator works is the radiation will interact with the material, or the scintillator, and that releases light. This light then propagates through the photomultiplier tube, and then reaches the computer where we analyze it. There are three types of radiation detectors. There are gas, semiconductor, and scintillators. Scintillators are used for this non-proliferation purpose. And then in scintillators, there are three types. There are crystals, which take a very long time to grow. They take months to grow, and are quite fragile sometimes. There are liquids, which are highly volatile in air and atmosphere and have a lot of mechanical parts, a lot of maintenance. Then there are plastics, which are really good for this application because they're chemically stable in air. They are solid and modular, can be transported. They can also be made into different shapes. And they're relatively inexpensive. So there are some drawbacks, including resolution. They have worse detection, but for the application of non-proliferation, they're the choice for the type of scintillator. So, again, we want to be able to use this in a non-proliferation application. So we're going to 3D print it. This is quick. It can be made into different shapes. So this can be printed in drones. This can be printed in seals carry around pens to detect radiation in different environments. Reactor parts, things like this that can't really be made in bulk. It's also less costly as well. So this is why we're 3D printing it. So to make a scintillator, I think a lot about making a cake. It's very similar. So we have our base polymer. This is the largest percentage of the scintillator. This does the legwork in the absorption of radiation and the energy transfer, and that's your flour. The primary dye assists that energy transfer into light, and that's your butter that gives it flavor. The wavelength shifter is, this shifts the wavelength from that primary dye and polymer. So it shifts it into a wavelength that can be read by the photomultiplier tube, be read by the computer. That's sugar, again, a flavor enhancer. And then a photoinitiator is, it kickstarts that polymerization. It kickstarts the hardening process. So that's your baking soda. You need the baking soda for your cake to bake. Crosslinkers. Crosslinkers are the chemicals that link the polymer chains together. So to keep your cake ingredients together, you need eggs. So you need crosslinkers to be able for the scintillator to harden. And then lastly, to detect thermal neutrons, we need a chemical that can detect thermal neutrons. So that's our additive. That's our vanilla here. Like many materials and research, there's competing interests. So twofold, we want this to detect radiation, and second, we want it to polymerize. We want it to harden. What do I mean? Well, when we look, there's also, in this research, we kept 3 of the ingredients the same, and then we changed the other 3. So the other 3 that we played around with and investigated are highlighted in yellow. So what am I talking about? So on the left, we have, out of our base polymers, we have PVT and PS. These are aromatic chemicals because they have a phenyl group, right, which is this like hexagon. These phenyl groups absorb and transmit energy in a very, very efficient way. So aromatic chemicals have very high radiation detection properties. On the other side are acrylates. So BMA and MMA, they have a methacrylate group here. They polymerize very quickly. However, they don't have very high radiation detection capabilities. Likewise, the aromatics don't print very quickly. So we have these competing interests that we need to balance in order to create something that, again, can detect radiation but also turns into a hard plastic. One thing to note is that BMA is really interesting because it has that methacrylate group right here at the top that is the same as this MMA that's used in 3D printing, but it also has this phenyl group. So it's kind of, we investigated the in-between chemical. And this hasn't really been investigated at all in scintillators. So now we have our base polymer that we're investigating. Well, we need our crosslinkers to make it into a hard plastic. Similarly, there are different types of crosslinkers. We looked at 2 of them. There's an aromatic crosslinker called DVB. Again, it has a phenyl group. It's aromatic. It has high radiation detection performance and takes a really long time to polymerize. And then PETA is our acrylate crosslinker, which has low radiation detection capability, but it prints very, very fast. What I did was I didn't want to choose between these 2, so I just combined them and created a mixed crosslinker system, which is our novel formulation in the crosslinker world. Last thing that we investigated was the thermal neutron dopant. We used lithium-6 because it has a high probability of capturing thermal neutrons, and it's chemically compatible with our formula. We had to synthesize this lithium-6 with an acid because to balance out the polarity, lithium-6 is a very polar chemical, which we then had to balance out with a very nonpolar resin. So we synthesized it with an acid called 3-PSA, which is why the actual dopant is lithium-6 3-PSA. So what did we do? I made the liquid resins in the chem lab, mixed all the ingredients together, I baked my cake, and then we synthesized the lithium-6, made lithium-6 PSA, 3-PSA, combined that into the original resin, and then took it to the 3D printer and printed it. Then we got these nice printed pucks. So we got these printed pucks, then we took them and tested them on multiple radiation sources to get our raw data. So this is our raw data that came out. Now what do we do? Now that we have data, what are we going to do with it? Well, this represents, this graph on the left, represents, this graph represents a singular interaction with the radiation and the scintillator. So this represents one count. We're going to call that one count. Then we're going to take the area under the curve. Whoa, calculus. And we're going to take the area under the curve, and then we get something called pulse area. Now, this represents one count. We're going to take all the counts. We're going to take all the counts and all of the pulse areas to get something called a Compton edge. Now, we can compare these Compton edges with the different scintillators. So we're going to find a quantity called relative light output, which is we take the Compton edge of our sample and the Compton edge of a commercially made sample that is equivalent in size and mass and these things, and we get a relative light output. So the higher the Compton edge, the higher the relative output, and the better detector that you have. So for our base polymer study, we looked at we looked at VT, styrene, BMA, and MMA. And from this, the trends indicate that the aromatics have a high relative light output, but cure very slowly. And again, the acrylates have a very fast polymerization time, but have a lower relative light output. We chose to move forward with vinyl toluene. It had the highest light output, and we wanted to have a preference towards that. Because what we can do is we can add crosslinkers to enhance that polymerization time. So we chose VT and didn't look further into styrene, BMA, and MMA. For the crosslinker, the mixed crosslinker system, we can see that as we increase the amount, the concentration of DVB, again, very similarly, the light output increases and the polymerization time is slower. And if we increase the amount of PETA in the mixed system, the light output decreases, but the polymerization time is faster. So I set it on a happy medium. I went 5 and 5, 50-50, 5% PETA, 5% DVB, to get the balance of the faster polymerization time and the relative light output at a good level. So we have our chemical formula. We decided on our monomer, our base monomer, and we decided on our crosslinker. Then we add in the lithium, and how do we discriminate the radiation? Well, I'm going to go back to our singular waveform. It's flipped this time, but we're going to take the integral of the end of that pulse, so the tail of the pulse, and we're going to divide it by the integral of the total pulse. This then gets us our PSP, our pulse shape parameter. We then take all of the counts. We take all of the counts, all of the PSP data, and put it onto this graph, where we can see that there's discrimination between neutrons and gammas. There's a neutron band here at the top and a gamma band there at that bottom. We take a slice of an energy range to then get this third graph here. And then from this graph, we can get something called a figure of merit. A figure of merit is a number that tells you how well the scintillator can discriminate radiation, so it can discriminate between gammas and neutrons. So our scintillator that we made has a figure of merit of 1.19 with the lithium-6. This is good enough for discrimination between neutrons and gammas. I didn't forget about thermal neutrons. So from these two graphs, we can see that on this graph with the lithium-6, there's this thicker band, this thicker cluster of points above this neutron band. And then we can see on this graph without the lithium, does not have the thermal neutron additive, that we don't get this thickening island of thermal neutrons. So with our scintillator that we made with this workable resin, we were able to discriminate all three types of radiation: thermal neutrons, fast neutrons, and gammas. Lastly, we wanted to validate that we can print shapes, so I printed a couple shapes. The logo, and then I printed a fish. So it works. It can print shapes, which is great, which is really great. In conclusion, I started this project 2 years ago, and we didn't have a resin that would even print in the printer, and it would take days to even thermally cure just with heat. And now we have developed a scintillator that can detect all three types of radiation. We created a novel crosslinker system, and we added lithium-6. And we printed a complex 3D geometry to prove that this works. This is our final formulation. For future work, we want to optimize this more, so the relative light output is still not where we really want it to be. We want to get that up to a comparable point with the commercial scintillators. And we want to look more into thermal neutron additives. The lithium-6 has solubility issues after 2%, though we can still see that we can still detect thermal neutrons. I still want that cluster to be more distinct and defined. Lastly, this is a picture of all the samples that I made. These didn't fit in that full picture, but all these pucks scintillate. They all glow, and that was my project this year. I just want to thank my advisors, thank the professors that are here, teammates, and friends that are here. So thank you. And my roommate's here. So thank you, everybody, and I would love to take any questions that you have. Thanks. Yes. Thank you. So that's a great question. We did have to balance the cure time with our other radiation detection properties. The thing that we did that helped out a little bit with determining that the margin there was that once, if the polymerization time gets really high or it takes a really long time, there's oxygen that comes in and quenches the radiation detection properties. So if, I don't know if I have, I can look at this. So if you look at this, like the DVB, this DVB sample with 10%, like DVB is supposed to be really good, have really good detection properties. It has a relative light output of 58%, but it takes 80 minutes to cure. Well, that oxygen is quenching some of that radiation detection property. So we see that, like, if we go down a little bit in DVB percentage and increase the PETA, then it polymerizes faster, and the oxygen doesn't have as much time to quench the radiation detection. So we see that this one is higher. So the little bit of PETA makes that radiation detection a little bit higher. So we have that limiting factor to help with the margin. So we can't just cure the scintillator for 2 hours and get a better scintillator, if that makes sense. Okay. Katie, can you raise your hand first? No, the printer prints in, the laser is like a UV light, so that UV light just makes it glow in general and scintillate in general. Again, these are conventionally baked in an oven, so they aren't exposed to like a UV wavelength radiation, so they don't need, for them to polymerize, they don't need to be exposed to radiation. They just, the light from the printer is just in the UV range, if that makes sense. Yeah. Professor Rosella. So a commercial scintillator can get around 3. We're at 1.19. It's that's about, yeah. Yeah, Ross. Yes, that's a great question. So there's boron 10 is a good one, and gadolinium. Gadolinium has like 3 times the probability of capturing neutrons. However, when we look at this graph here, the boron 10 and the gadolinium will, when it captures a neutron, it releases gammas. So that makes discrimination really hard when you have this capture additive that releases gammas while also when it's trying to show that we can detect thermoneutrons. Lithium-6 doesn't do that. It releases an alpha, and that doesn't mess with anything that's going on with the gamma band and the neutron band. Yes, sir. Yes. The thicker the puck is, or the thicker your scintillator is, the better detector it is with the photomultiplier tube. When we print shapes, as long, I mean, again, it's more of a factor of thickness of how much that measurement is than the shape. The shape generally, if it just covers the photomultiplier tube entirely, then that's good. That makes sense. Yes, Professor Raghi. Yes. Yes, sir. I'll be doing simulator work there, so I really love this work. I love the hands-on work, and I'll continue that at Berkeley at their simulator lab and working with Livermore. Thank you. Thanks.
Mike. I was the lead Trident midshipman, soon-to-be officer, and phenomenal. A little bit of context of what he's doing, both on the commercial side and government side. So you're going to hear about what he actually did here, but what I've seen is within 5 years, you're going to see the technology that he presents will actually be flying us and beaming actual power down to Earth. So this is actually real research that you will see. So when you watch his presentation, look for in the next 5 years that he is on the cutting edge of what will be done. And so keep that in mind, that the Trident program is actually doing this for him. And I hope that he continues this research as he looks forward, both in the Navy as a pilot, and then further on, I know he will go on to graduate school and do. So I want to introduce, spent learning a lot, educating me along with my advisor, Professor Nelson, and please keep in mind that this technology is going to be out flying within the next 5 years.
I'm William Hardaway, and I'm incredibly excited to share with all of you what I've been working on for this past year. That being my Trident report, and it's titled Integrating Power Beaming and Communication with Laser Diode Modulation and Multi-Junction Photovoltaic Cells. So there's a lot of words there. Let's start by breaking it down by what I mean by power beaming, and what that actually means for my research. So I'm focusing on laser power transmission, LPT for short. These power beaming technologies function by using lasers, typically laser diodes, to beam power onto solar cells, or photovoltaic cells, PV for short. These systems operate at distances typically from hundreds to thousands of kilometers and have magnitudes of power transmission up to megawatts. These systems essentially allow us to outsource the power generation and storage capability for any kind of electrical system or vehicle, whether that be on the terrestrial or space-based side. It allows these systems to decrease the size, weight, and power of their subordinate capabilities, decreasing mission architecture complexity, decreasing costs, making them altogether a more survivable platform. It's already being integrated into commercial and defensive platforms, whether that be NASA and using it for lunar rovers to explore the moon's surface and the dark recesses of lunar craters, or military applications for ISR UAVs, allowing us to beam infinite power, establishing essentially infinite endurance platforms within enemy territory. Okay, a little bit brief of why we haven't seen laser power transmission until very recently. And that's because the power has to be transported and transformed through so many different subsystems before being transmitted across hundreds of kilometers where it's attenuated, and then transformed some more once it's received. Each of those different transformations comes with its own inefficiency. We are losing power all along the way, which you can see with this graph here. However, LPT is finally becoming a mature technology where each subsystem is being iterated upon such that the individual efficiencies are finally at the point where the end-to-end efficiency of the platform is commercially viable, whether that be laser diodes going from a 10% efficiency to over 60% nowadays, or solar cells and PV cells going from 20% in the early 2000s to over 50% nowadays. All this to say that LPT is a mature technology that we're seeing more and more of, and my research hopes to iterate and advance that technology to the next level by integrating a communication system into these pre-existing technologies. So what does that mean? Essentially, you're modulating the laser diodes that you're transmitting the power with to different power levels. Each of those power levels is associated with a bit, essentially allowing us to establish a communication link with the solar cell that we're transmitting to. Why haven't we seen this before? Well, it's because LPT systems, like I said, suffered from end-to-end inefficiencies. And intentionally modulating your laser diode decreases the power transmission that you're sending, essentially adding another level of inefficiency. If you see right here at this red arrow, this is where we're adding an additional inefficiency to the system. However, because the system is finally mature, we can intentionally add this to the system and still be commercially viable for both commercial and military applications. Okay, a little bit of vegetables before we dive in and establish background as to how we analyze these different subsystems. Starting off with our PV cells. PV cells operate by using a lattice of crystals that take photon energy and transmit it into usable electrical energy. Each different type of lattice responds at a different efficiency to a different specific wavelength. Modern PV cells have been able to establish their higher efficiency because they stack multiple of these different types of lattices on top of each other, allowing them to capture at higher efficiencies different wavelengths, allowing us to essentially use more of the energy of the sun's broad wavelengths of lights. Then we also have an IV curve, just for your situational awareness. This is what we typically use to analyze the performance of our PV cells. Long story short, we're aiming to operate at the knee of this curve where max power is. And what that means is we just have to match the variable resistive load that we attach to the PV cell in order to operate there. Okay, my research itself iterates upon NPS simulations conducted in the late 2010s. They simulated a modern triple junction PV cell under solar and laser power. Their results indicated that if they used laser diodes matched the specific wavelengths of each of those lattice structures in the triple junction cell, they could increase the base efficiency of the PV cell compared to its performance under sunlight. My research uses this simulation to create an experimental version of it, not only to validate their research, but use it as a platform for modern advanced LPT power beaming systems that I can then integrate my modulation sequence into. And then this is the specific wavelengths that they used to match to the triple junction cell and the variable different power apportionments that each laser diode would receive in order to operate at peak power efficiency. Okay, now that we have a semi-firm foundation and we can kind of speak the same language, let's dive back into what this research is actually about, integrating the LPT system with the communication system. Once again, we're using that LPT system that I'm creating from the NPS research and modulating the lasers to create a communication link. This has to be constrained by maintaining the high power efficiency of the LPT system while also establishing high-speed communications. We'll be doing this using a multi-junction PV cell, specifically the same triple junction cell modeled by NPS, as well as multiple laser diodes, each matched to the different layers of the PV cell. The process of the research unfolded through 3 different phases, the first being developing the modulation and communication link that we'll be using an LED system. We then developed the actual LPS structure and validated the NPS research, and then finally integrated that LPT system with our communication architecture for a single package. Okay, starting off with developing the modulation sequence itself. So, as I said earlier, in order to use your laser diodes to communicate with your PV cell, you're lasing them at different power levels. Each different power level is associated with an amplitude, which can then be associated in turn with a bit, whether that be a 1 or a 0. A very simple version of this communication is on-off shift keying, where you only lase the laser diodes at 2 distinct power levels. Your highest power level would be associated with a 1 being transmitted, and a lowest power level being associated with a 0 you're transmitting. Rapid modulation between those power levels allow you to send 1s and 0s to your PV cell, establishing that communication link. My research hopes to iterate upon that and instead use an MRA amplitude shift keying modulation scheme. What does that mean? Instead of just using 2 different amplitude levels, we'll be using multiple, hence the M in MRA. For example, if you use 4 different amplitude signals that you can send, that's associated with 4 different symbols that the PV cell can read, that means that each of those signals will be associated with 2 bits of information according to this equation here. So the more symbols that you can send, more differentiable amplitudes of power that you can transmit, the faster you can communicate. Okay, to simulate this amplitude shift keying system, we used a function generator externally modulating an LED light using a square wave, where a square wave, each amplitude was associated with a different modulation power signal being sent to the system. We used different square waves to then simulate different amplitudes and different variable schemes of modulation. Finally, for the LED testing, we were able to create these results. Not amazing, but the important thing to note here is that the communication structure was able to distinguish between the different amplitude levels, establishing a communication link. With that in mind, we immediately jumped into developing the LPT system itself. This here is the final iteration of the construct after more iterations than I care to omit, but the basic idea is that you have 3 laser diodes, all of them focusing and irradiating a single PV cell, our triple junction cell. That cell feeds into a circuit that allows our data acquisition device to read the variable voltage levels of our PV cell. That voltage signal is then fed in to be read as our communication signal, whether that be 1s and 0s or whatever. We also used a function generator similar to the LED experiment to externally modulate the lasers to introduce that communication scheme. This is what the structure looks like in actuality. You can see the top with it powered on and the lights off. Unfortunately, only one of the 3 laser diodes operates in the visible spectrum, so although all 3 of them are currently lasing, you can only see the 520 nanometer laser. This is a quick diagram of what the DAC circuit looks like. Of importance to note, we have 1 ammeter and 1 voltmeter independently verifying the results of our data acquisition device and our PV cell here. We also have a variable resistor load used to match the resistance of the PV cell, so we're operating at peak power efficiency, if you remember what I was mentioning about the IV curve. Okay, MPS said that these 3 wavelengths we have to operate at for peak power efficiency: 555, 860, and 1510. Due to the limitations on the commercial side of what is actually available, we ended up using a 520 nanometer, an 853 nanometer, and a 1455 nanometer laser diode. So closely matched, but not perfect. Before introducing this specific PV cell into our LPT structure, we first measured its power efficiency under normal sunlight. We did that by placing it in a solar simulator and then identifying its peak power efficiency. Under normal sunlight, the cell was operating at 20.5% efficiency. We then placed it into our LPT structure, and through iterative testing, we were eventually able to establish a maximum power efficiency of 32.9%, validating the MPS research that we can in fact increase the base efficiency of a triple junction PV cell with LPT laser diodes. Okay, this right here shows the different testing that we did with the LPT system. Important to note that what we learned was, as you increase the incident illuminated area of the PV cell, our power efficiency increased. As we increased the amount of power that we were sending to the PV cell, the power efficiency increased. And the peak power efficiency was established when those laser diodes were transmitting at the power apportionment levels stipulated by NPS, where one laser had 50% of the power transfer, another 30%, and the last one roughly 20%. This allowed us to have the peak power efficiency of the PV cell. Any deviation from those relative power apportionments led to dramatic decreases in the power efficiency of the lasing system. Okay, now that we knew the base power efficiency of the cell, we wanted to determine how power efficient it would be in a modulation sequence. We used 4 different modulation methods at a depth of modulation of 5%. So what that means is we were modulating the laser diodes from 100% power to 95% power. And we're going to determine how efficient a modulation scheme introduced in that system would be while modulating between those power levels. So the 4 different methods were, the first one we were combined modulation scheme of all 3 laser diodes being modulated simultaneously, where they maintained the relative power apportionment as they decreased from 100% lasing power to 95% lasing power. The other 3 iterations where we were only modulating a single one of the laser diodes, each of them taking the full brunt of a 5% drop across all 3 or total laser power. Ultimately, we found that the most effective means of modulation was single modulation of the 520 nanometer laser diode. This allowed us to maintain high power efficiency while also introducing a less complex system that could be more easily worked with and malleable, ultimately creating a total power efficiency for an integrated system of 31.6%. When you compare that to the original maximum power efficiency of 32.9%, we see that this communication architecture itself is 96.1% power efficient. So we're losing 3.9% of our total power by introducing this modulation scheme. Now that we had the LPT system working and we had our basic communication structure, it was time to actually integrate the real modulation scheme into the lasing system. So in order to communicate at our fastest possible speed, there's 2 different factors that we have to account for. The first being how quickly we can modulate between the different amplitude levels of our laser diodes, and the second being how many different amplitudes we can introduce into that modulation structure, whether that be only 2 levels, 4, 10, etc. The speed with which we can modulate between the amplitudes is dictated by the time or settling time it takes to go from your maximum amplitude to your minimum amplitude. That's essentially the largest distance it has to travel. Under this system, we found that the settling time for the LPT system was 4.5 milliseconds. We'll go into why that's a little slow a little bit later, but that essentially established the speed limit for our system. So we were able to modulate with a 5% modulation depth at a speed of 200 hertz. So speed limit established, it was time to go into what the minimum step size we could establish between amplitudes were, so we know how many different individual amplitudes or symbols we could introduce into that laser system. So this is a modulation at 0.5% maximum lasing power. And as you can see, it's not looking great. A lot of noise there. It's kind of wiggly, washy, not very pretty step waves. We eventually, after lots and lots and lots of testing, were able to determine that this isn't actually from the LPT system or the PV cell. It was being internally added by our data acquisition device. So the only solution we had without buying a new DAC was to post-process this information. So we had to measure the noise produced by the DAC with the PV cell unpowered. That's right here, and characterize it as a sine wave. That, coincidentally, is a 60 hertz sine wave, which, as you can imagine, same exact frequency as your power output, which, yeah, our DAC was messing us up. So the only way to post-process that was to characterize it, match the phase and amplitude to our intended signal, and cancel them out. That gave us this with our uncorrected version on the far left, yikes, and then the corrected version on the far right. So we were able to clean it up a little bit. The red regions here indicate when the signal is actually being sampled by our system to determine what communication architecture is being sent. So we were able to clean up the signal, establish our minimum and maximum step size. The next step was then to determine this communication modulation scheme we developed, what's the efficiency or bit error rate that the system introduces. So we did that by measuring the voltage at two discrete amplitude levels at their closest gap, that being 0.5% or minimum step size. Each of those voltages for those intended signals are displayed here and here. As you can see, they form a Gaussian and normal distribution. So to determine what the bit error rate or the detection error that we'll be introducing with the system is, we characterize these as normal distributions and then see how much of that area overlaps each other. That area is proportional to our bit error rate. And we use these two equations to figure that out. But ultimately, our bit error rate ended up being 2.45, 10 to the negative ninth. What does that mean? It means it's incredibly small and almost nothing. So bit error rate, good to go. Signal can effectively distinguish one another. Taking it all in totality, the communication structure that we developed here was able to modulate at 200 hertz, establish 11 different distinguishable transmission amplitudes, leading us to have each signal or symbol being sent contain 3 bits. That, taken into this equation, gives us that our communication structure was transmitting at 600 bits per second. So, okay, we'll get into why that's not as fast as I would have liked. But overall, the total results of this experiment were communication speed of 600 bits per second, bit error rate of negligible amount, communication power efficiency of 96.1%, and an integrated power efficiency of the entire system operating at 31.6%. So a quick reason as to why we weren't able to transmit or modulate as fast as I would have hoped, that being the noise introduced by the DAC system. We were only really able to distinguish at levels of differences of 5 millivolts within the transmission signal. Ideally, we'd be operating in the microvolt region. What that allows us to do if we can distinguish voltages at a finer level is that we can reduce the maximum amplitude modulation depth that we're operating at. A smaller maximum step size means that the settling time is faster, meaning we can modulate the system even faster. Not only does this increase the communication speed, but it also increases the power efficiency because you're modulating the laser diode even less. Also, an advantage of a more refined DAC system is that we can also decrease the minimum step size of the system. A smaller minimum step size means that we can introduce even more distinguishable amplitudes and symbols into the system, meaning that we can transmit 5, 10, 15 bits per signal being transmitted, dramatically increasing the speed of communication. Nonetheless, this research was able to effectively validate the simulated results from NPS while proving the capabilities of integrating communications with a modern LPT system. This can effectively feed into the new applications that we're seeing in LPT power transmission, whether it be for terrestrial means, powering remote areas on the planet using blimps, or our space infrastructure and power beaming across different satellites or space-based infrastructures, or our military-industrial complex and how that can help support our UAV industry. With that being said, I'd like to thank all my advisors and friends for supporting me this past year, and I'll finally quit babbling and open the floor to any questions you might have. Thank you so much. Yes, ma'am. Of course.
So you talked about, in the end, you were going with a three-bit transmission. It only requires 8 levels.
Yes, ma'am.
So the fact that you were able to get 11 amplitude, I mean, are you building in some buffer there, or why not already kind of reduce the amount of modulation to just get 8 levels?
Yeah, it was mainly redundancy, and also just the lasers were a little bit difficult to fine-tune to the precise levels. So under a real application system with a 3 bits per signal, we would just eliminate those extra 3 amplitude levels. And instead of operating at a 5% modulation depth, it might be a 4.5% modulation depth. Thank you, ma'am. Yes.
As this technology progresses and gets integrated through the military through ISR, how susceptible, if at all, is this to interception of message?
Of course, yeah. This isn't the first time that we've used lasers to communicate. Actually, coincidentally, we used it during the Artemis mission itself. What's novel about this is that we're using the laser to communicate and using it to power the system. So laser transmission for communication is a fairly well-developed technology in and of itself. And just like using radio waves to communicate, you're just modulating a radiation signal, essentially, and decoding that modulation scheme. The advantage of lasers opposed to using some radio signals is that it's refined and localized. So the enemy has more problems receiving the signal because it's not being broadcast across the entire area. It's being effectively lased to a single location. So the only way to intercept this signal is to physically go in front of the laser and block it. And when it's blocking the signal, then, okay, not only do you know that your system is not receiving power and it's not receiving comms, but you know there's something in the way, so you can eventually just immediately cut off your comms. Also, kind of aside, laser diodes or laser comms have been shown to be able to communicate at a faster rate. So it kind of helps us in both regards. Thank you. Yes, sir. Sure. That goes back to the NPS research. Let me see. I'll go back to this slide. This one. So since it's a triple junction cell, we have 3 different lattice structures there. So each of those lattice structures has a wavelength that it's most efficient at operating. And the reason why the LPD structure has a higher efficiency than sunlight is because we're cutting out all those extra wavelengths that the cells are not as responsive to and lasing at those 3 specific wavelengths that it's most efficient at. That's why we're using those 3 different laser diodes, each operating at a wavelength associated with one of these levels in the PV cell. Oh. So that's what our original PV cells were back in the early 2000s, just basic silicon cells. We've been iterating upon that technology because we want our PV cells to also work under sunlight. So the advantage of this system is that we can integrate it with pre-existing technologies that are already out there using the sun to power themselves, and then we can just throw in subsystems operating in orbit or on terrestrial applications that operate with the pre-existing technology and can laze to these cells and help support them in their actions. Thanks, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir, absolutely. For long-range power beaming, there are actually 2 primary methods, LPT, laser power transfer, and MPT, microwave power transfer. So there are distinct advantages between the 2. The advantage of microwave power transfer is that, kind of hit the nail on the head, the lasers that operate at these distinct wavelengths are attenuated at the atmosphere. That's why they're most applicable for space-based applications where we have no atmospheric attenuation. Microwave power transfer operates at wavelengths that the atmosphere doesn't attenuate, and it's a slightly more developed technology. It's been around longer, so we have the systems already in place to transmit at high power levels. However, LPT systems themselves have the potential to be beaming at larger magnitudes than MPT right now. And I absolutely believe that China was operating that. We've already had NASA and DARPA conduct similar operations with UAV unlimited endurance power transfer. Thanks, sir. Oh, yes, sir. Yes. Yeah, it sets our speed limit for our modulation system. I'll kind of mention it with the data acquisition device, and that our discernible voltages with this equipment was only 5 millivolts. If we could have smaller discernible levels, ideally microvolts, we would be able to decrease the modulation depth of the entire architecture. What that would mean is that we, instead of modulating between 5%, we might have our maximum step size be 0.5%. That essentially allows the system to settle faster because it's traveling, think of it traveling less distance almost. A finer attuned modulation depth means faster settling time, which means that we can modulate it faster without cutting off the square waves. And I also suspect that the settling time was even for this voltage disparity is likely faster, and that the data acquisition device itself is likely not keeping up with the PD cell. Thanks, sir. Okay.
We have a few minutes before our next speaker is at 9:45, so help yourself to some drinks there or a break. See you back here at 9:45.
Thank you.
All right, thank you, Dr. Nutt, and good morning, ladies and gentlemen. As he said, I'm Nicholas Ciascio. Thank you all so much for being here. Today, I'm going to talk to you about my Trident research in my study titled One-Way Attacks Against Surface Ships, Learning from World War II and the Russo-Ukrainian War. All right, so let's start with two cases of one-way attack attempts against the Russian Black Sea Fleet in the Black Sea since the Russian full-scale invasion in 2022. So jumping back to August 1st, 2023, two Russian ships were transiting through the Black Sea when they were attacked by 3 Ukrainian drones. In this attack, Russia used their self-defense systems on board of their ships to destroy all 3 of these drones. Now, jumping ahead 2 years to August 28, 2025, a Russian missile corvette was transiting through the Sea of Azov when it was attacked by Ukrainian one-way attack systems. In this attack, the Ukrainians were successful and they're able to damage the Russian missile corvette. So were these 2 attack attempts different in their outcome? So this ties into my research question for what I've been looking at in my Trident research over the past year. So I ask, under what conditions do attackers using one-way attack systems succeed against surface ships when ships are operating near attacker-held territory? So to give you a preview for the rest of my presentation, I'm going to start by telling you exactly what one-way attack systems are and the 2 different examples that I'm looking at in my research. Then I'll tell you about my dependent variable. After this, I'll go into existing explanations and hypotheses for my 3 key variables. After this, we'll go into my first case, which is the Battle of Okinawa. Then my second case, the Russo-Ukrainian War in the Black Sea. After this, we'll talk about some findings, relation to 3 big conflicts, and then implications for the fleet, and then lastly, some lessons I've learned from this process. All right, so what are one-way attack systems? So a one-way attack system, as I define it in my study, are systems with a single-use mission designed to strike targets directly with an explosive integrated warhead. And the main goal of these systems is to damage whatever the target is in this research, specifically surface ships. So the 2 key examples that I'm looking at in my studies are Japanese kamikaze aircraft and modern Ukrainian drones. All right, so what exactly am I trying to figure out here? So I'm looking at the success or the failure of one-way attack attempts at the tactical level, specifically when a one-way attack system like the kamikaze aircraft or like the drones are attacking a ship or a small formation of ships. All right, so I'm looking at 3 key variables which may help to answer my research question. So first, the attacker's skill school. So in this school, scholars say that attackers can succeed when the pilots or operators make better use of their own skills. So the way that I attempt to look at that in this research is through the use of terrain and environmental features during an attack. This can include when attackers fly in the clouds when it's overcast, when they use a mountainous backdrop, along with a handful of other examples. The second school, the attacker number of assets school. So this one, scholars say that success rates can increase when the number of attacking units within an attack attempt increase. So this specifically refers to mass attacks when there are 2 or more one-way attack systems involved in the attack attempt. And then lastly, wartime learning. So this is when forces learn, innovate, and adapt over time throughout the conflict. And in doing this, they make changes to improve their odds of success. So now let's link these 3 key schools of thought to 3 hypotheses for this research. So first, when attackers use their skill, specifically the pilots and the operators, they may be able to improve their concealment, reduce their chances of being detected by the defensive forces, and reduce warning times of an attack, ultimately leading to higher success rates for the attackers. Next, in the attacker number of assets school, if mass attacks are used in a one-way attack attempt, this will overwhelm and saturate the targeted forces systems, which may lead to a handful of different things coming from that, including coverage gaps, slow reaction times, and reduced accuracy of the defensive system, again, ultimately leading to improved success rates for the attackers. And then lastly, with wartime learning, this school, or this hypothesis, relates to both or it could relate to either or both the attacker or the targeted force. And this is when forces can learn lessons throughout the conflict, reallocate their time and resources, and then ultimately lead to higher success rates for either force in the conflict. All right, so what are the two cases that I'm looking at? So I tried to find cases which were naval engagements that were in or near adversary-held territory. This can also be referred to as contested zones, which is a term coined by scholar Barry Posen. So my first example of one of these naval engagements is the Battle of Okinawa, which I'm specifically looking at from March 24th to June 30th, 1945, during the Pacific Campaign of World War II. So in this conflict, and in this case, I'm specifically looking at Japanese kamikaze aircraft attack attempts against the American Pacific Fleet in or near the Okinawa coastline. In this battle, because it is a historical conflict that occurred more than 80 years ago, we have better, more accurate, and more verifiable data that allows for strong and solid analysis on this case. My second case, the Russo-Ukrainian War, which I'm specifically looking at in the Black Sea and in the years of 2023, 2024, and 2025. And this is Ukrainian drone attack attempts against the Russian Black Sea Fleet in the Black Sea. With this case, there are more data inconsistencies and there are some data availability issues. This is mainly because it is a current, ongoing conflict, and if Russia or Ukraine was to release accurate and verifiable information about the conflict, this may create a strategic issue for them moving forward in this conflict. All right, first case, Battle of Okinawa. Before we talk about it, let's go back a few months to October of 1944 in the Battle of Leyte Gulf. So in this battle, the Americans were coming up along the Japanese coast. Japan knew that unless they made some changes, they may have to surrender very soon, so they became desperate, and they turned to kamikaze aircraft. They compiled all the pilots they could find, all the aircraft they could find in order to do one-way attacks against the American Pacific Fleet. Over the next few months, they continued to do these kamikaze attacks, improving their tactics, gathering more pilots, more aircraft, ultimately leading to the pinnacle point of kamikaze usage in the Battle of Okinawa in the spring and summer of 1945. So for this case, how did I collect the data? So first, I looked at primary source ship's logs from Records Group 38 at the National Archives. So these ship logs were written in real time by U.S. Navy sailors on board of American vessels during the battle. So Records Group 38 has digitized most of these records, and I was able to go through many of these different ship logs, pull observations of kamikaze attack attempts from there. After this, I turned to the Divine Wind, which has an appendix with about a little more than 100 kamikaze attack attempts during the Battle of Okinawa. However, it does focus more on successes, and it has fewer observations than what I was looking for, but I pulled some observations from there. After that, I turned to other secondary sources to gather both new observations and pull supplemental information for the observations that I already had. Some examples of these secondary sources included the Naval History and Heritage Command and Pacific Rex. After this, I disaggregated the data, cleaned it, and ended with 484 kamikaze attack attempt observations. All right, now let's look at some descriptive statistics from my original comprehensive handmade data set. So in the 484 observations, 157 were seen as Japanese successes when Japan was able to damage or destroy a U.S. vessel and or U.S. personnel on board the vessel. There was 327 failures when they were unable to do this, leading to a split of about 30-70, which falls roughly in line with what historians say was the success rate of kamikaze attacks. All right, now, let's tie back into the three hypotheses that we discussed previously. So first, for attacker skill. In my data set, 61 observations were identified as having a time when the kamikaze pilots skillfully utilized terrain or environmental features in their attack. Like I said, this could include if they flew in the clouds or if there was a mountainous backdrop or anything along those lines. In these 61 attacks, they were successful 57% of the time, and in the times when they were not identified, as using the terrain or environmental features. They were successful 29% of the time, leading to a difference of about 28 percentage points. So that's the quantitative evidence for this hypothesis. There's also a plethora of qualitative evidence located in the ship's logs and other sources, as seen in the quote on the screen, discussing when the kamikaze pilots used their skills. All right, hypothesis 2, the one that relates to mass. So in the 249 attack attempts in my data set where the kamikazes, or the kamikaze corps, used 2 or more kamikazes in their attack attempt, they were successful 41% of the time. In the 235 attack attempts when there was a singular kamikaze, they were successful 24% of the time, leading to a pretty big difference of 17 percentage points. This in itself is interesting, but it's also important that we look at success rate versus the number of aircraft used in an attack. So let's look at the relationship between these two elements. So on the left side of the screen, we can see a graph. And when we go between 1 and about 8 kamikaze aircraft utilized in the attack, we can see the success rates increasing from about 30 to 60%. But then from about 8 until 29 aircraft, the success rates stay pretty stagnant at sitting around 60%. After 29 aircraft, the success rates begin to increase again. So this shows that there may be a non-linear relationship between success rates and the number of assets used in an attack. And then lastly, similar to the skill hypothesis, there is a lot of qualitative evidence both in the ship logs and in other sources from historians and scholars which indicate how successful the mass attacks were. All right, lastly, for the learning hypothesis, hypothesis 3, I attempted to look at wartime learning during the Battle of Okinawa through the lens of success rates week by week during the 14 weeks of the battle. I looked at it at the tactical level, and in this graph we can see on the left-hand side, the success rates seem to go up and down almost at random, peaking at a little more than 40% from some weeks, and then lower than 20% for one of the weeks. However, it's important to note that there are many other factors which may have played into wartime learning, both at the tactical and the operational level. I also ran a logistic regression model for the Battle of Okinawa, and the two key things to pull from this model: first, for the skillful usage of the terrain variable, which is seen as significant, this model shows that when the kamikaze pilots utilized the terrain, they were about 5.4 times more likely to be successful than when they did not. And then the second big finding from this model is that as the number of attackers increases in an attack attempt, the chances of success for the kamikazes increased by about 8.5% for each additional aircraft. All right, now let's jump into my second case, more modern, the Russo-Ukrainian War. So the Black Sea has been an area of power, control, and influence for thousands of years. And this was especially important during the Russian full-scale invasion of Ukraine in February 2022. So at this time, Russia not only looked to have control over the land domain, but also the naval domain. And at the beginning of this conflict, Ukraine had almost no surface fleet within the Black Sea, while Russia had a surface fleet dedicated solely to the Black Sea Fleet. So because of this difference in fleets within the Black Sea, Ukraine had to turn to an alternative method to combat the Russians, and this included launching thousands of drones to combat the Russians. All right, so similar to the Battle of Okinawa case, I collected data where I started with the Ukrainian source, Black Sea News, which has many databases regarding Russian and Ukrainian missile and drone attack attempts in the Black Sea. I pulled observations from that source. After this, I turned to Russian and independent sources, where I pulled more observations and cross-verified the data that I already had. After this, I disaggregated the data and cleaned it, and ended with 95 total Ukrainian drone attack attempt observations. All right, so let's look at some descriptive statistics for this case. In the 95 attack attempts, 39 were identified as being a Ukrainian success, where they either damaged or destroyed a Russian vessel and or Russian personnel. 56 were Ukrainian failures, leading to a split of 40 to 60. And 2023, in my data set, has the most attack attempts with 52 attacks. All right, so hypothesis one, relating to skill. I looked at this from a qualitative lens, and because of the importance of this conflict in the 21st century, many scholars, veterans, and analysts have looked into the different elements of this conflict. To give one example of a scholar and a veteran talking about skill within the Ukrainian drone operators, Maria Berlinska says some 85 to 90% of drone success depends on the people, and this includes the operator of the drone. All right, now let's go to hypothesis two regarding mass. So in my data set, 68 attack attempts had 2 or more Ukrainian drones involved. They had a success rate of 43%. Now, when there was a single Ukrainian drone involved, in my 23 observations in my data set, their success rate was only 30%. But again, similar to Okinawa, we must look at this from a different lens, where we look at the relationship between success rates and the number of drones used in an attack. So as we can see in the graph on the left-hand side of the screen, between 1 and 11 drones, the success rates stay roughly around 40%. However, when we go from 11 to 15 drones, the success rates increase by about 15%. And then from 15 drones or more, the success rates stay high at 50% or greater. This again indicates a non-linear relationship between the number of assets and success rates. All right, hypothesis 3 regarding learning. So I looked at this from the lens of year-by-year successes for the Ukrainian drones in their attack attempts. So in 2023, we see a somewhat low success rate of 29%. Then it jumps to 50% in 2024, then 86% in 2025. So as we can see, at the tactical level, there was a pretty sharp increase in success for the Ukrainians. It's important to note, though, at the operational level, there were some other elements that go into wartime learning which may relate to this finding. One example of this is that early on in the conflict, the Ukrainian drones and missiles were such a threat to the Russian Black Sea Fleet that many ships within the Black Sea Fleet were either sunk, damaged, or had to get pulled back closer to the Russian coast away from the Ukrainian coast. All right, I also ran a logistic regression model for the Black Sea case. So as we can see here, the month of the attack, or the month that the attack occurred, is seen as significant. And as we can see, as the month goes on within this conflict, the success rate increases, potentially indicating that the Ukrainians learned throughout the conflict. All right, so let's take everything I said over the last 10 minutes and put it in one comprehensive table to go over my findings. So first, for the attacker skill school, 4 of the 6 categories of evidence support the theory that attacker skill has an influence on success. Because 4 of these 6 categories support that and 2 are inconclusive, I find that attacker skill has likely influence on success rates. Next, for the number of assets school. 5 of the 6 categories of evidence have evidence which supports this theory, and 1 is inconclusive. Because of this, I find that the number of assets used in an attack, specifically mass attacks, has a likely influence on success rates. And then lastly, wartime learning. The evidence is a little more all over the place for this school. A couple categories of evidence support this theory, a couple do not, a couple are inconclusive. So because of this, I find that it is inconclusive based on the data that I've collected if wartime learning has an influence on success rates. All right, so how does this relate to other conflicts going on in the world or conflicts that may happen in the future? So first, the Iranian conflict that's currently going on and it's all over the news right now. So we've seen Iran launching one-way attack attempts, specifically with drones, against tankers in the Gulf region. It's only a matter of time before they launch more and more and more attacks, potentially against U.S. ships transiting through the area. But some groups have already started launching one-way attack attempts, specifically with drones, against U.S. ships, and these are the Houthi rebels. So they're launching UAV and USV attack attempts against U.S. ships transiting through the region. Lastly, the China-Taiwan conflict. So China has a very large military-industrial base, and they will have the ability to produce millions of drones to utilize if a conflict between China and Taiwan ever occurs. If this conflict occurs, we will absolutely see pretty high levels of drone warfare. All right, so what are the implications of this research for the U.S. Navy? So I have come up with 3 key elements of my research that I believe are important for the U.S. Navy. First, based on the Attacker Skill School findings, our drone operators must be highly skilled and they must receive the highest levels of training. They must know how to evade radar systems, other sensors, and weapon systems. And this can come from learning from practitioners who have already seen drone warfare in conflict, such as sailors on board of the USS Carney. And then second, our policymakers and military leaders must be able to determine the correct number of drones to utilize in an attack. So as seen in both of my cases, there's a non-linear relationship between the number of assets used and success rates. Because of this, there may be a chance that there's diminishing returns in these one-way attack attempts. And based on this, using too few or too many drones in an attack may not be effective. And then lastly, our policymakers, military leaders must understand that one-way attack success is not solely about technology. It also is about skill, utilizing the terrain, utilizing the environment, and knowing the correct number of drones to use in an attack. All right, so what did I learn from this research? So I obviously learned a lot, but I'm going to cover 4 key things that I've learned in this research. So first, data availability issues. I went into this project hoping to look solely at the Russo-Ukrainian war. I learned pretty quickly that the data was not great, that it varied between the Ukrainian side, the Russian side, the independent source side. So I decided it would be better if I turned to a historical case first, hence why I turned to the Battle of Okinawa. I learned that modern and current conflicts have some data inconsistencies that must be worked around when doing this type of research. Second, I had to learn how to frame the research. So I was able to collect the sources, I was able to collect the data, I was able to analyze the data, but I really had to understand how to frame my research around policymaker and literature debate. Third, I had to figure out how to distill and condense all the information that I have. So I've been working on this project every single day since August. It's a lot of information, and it's a lot to condense down. I have hundreds of documents and spreadsheets on my computer that relate to this research. And for example, in the bottom left of the screen, that's me talking at the USNA Board of Visitors meeting a few weeks ago. I gave a 3-minute presentation there, so I had to take all the information that I have, condense it down into a 3-minute conversation. Right here, I had a little bit more time. I think I had about 15 minutes, but that's me as a panelist at the International Studies Association annual convention about a month ago in Columbus, Ohio. But even there, when I'm talking to scholars who know a lot about these cases, I had to still be able to condense all my information down into 15 minutes and make it meaningful for them. And then lastly, I had to learn how to format my paper for publication. I've obviously written papers within my political science classes here at the Naval Academy, but I'd never written a paper where it had to be written and framed for publication. I had to learn how to do that and spend a little more time learning about that process. All right, so thank you all so much for coming. I really appreciate it. I'll take any questions you have now, or I can be in the lobby after to answer questions. Thank you. Ma'am.
Thank you very much. I love it. I love
So, ma'am, I have a few different thoughts about what may have led to that sharp increase that we saw in the success rates. One theory that I have is that the Ukrainian forces, as well as the Russian forces, are able to learn in real time. Obviously, the resources and the capabilities, especially with the technology that those forces have now, is much better than what was available in the 1940s. The U.S. ships and the kamikaze corps in 1945, because it was such a short conflict of only 14 years, were not necessarily able to learn on the fly and to learn as they go. They might go out for a couple months at a time. They really didn't have the technology to communicate the different lessons that they were learning. So I think that the communications and the technology that modern forces have really helps with that. I mean, in the news we can see different measures, different countermeasures, different tactics being taken by the Ukrainians and the Russians almost weekly at this point. So, yeah, the technology and the communication absolutely plays a factor into that difference. There's also so many different types of drones that the Ukrainians have been using now, and so many different tactics that they have, whereas the kamikazes were fairly black and white with the way that they conducted their kamikaze attacks. So I believe that also may play a factor into that. Sir? So that's the success rate. I'll go back to the slide, sir, if you don't mind, just so I can show it a little better. So this is the success rate with the number of drones utilized or more. So what I mean by that is when we see this data point at 5 right here, that's when the Japanese kamikaze corps had 5 or more drones in their attack. Then next we would look at when they use 6 or more drones in their attack. And that's just when I say success rate, that's just within those observations which fall within those parameters, how often they were successful in their attack striking the ship or the... Absolutely. In this research, I'm considering it a 100% success rate that as long as one kamikaze or one Ukrainian drone struck the ship, damaged or destroyed it, then that's a success for them.
I was just curious if you reached out to Aries or before and performed any research, because I know Aries kind of cutting edge stuff in the war training background as well. And before just stood up their drone attack.
I did not. However, I am doing this research, or I'm going to continue to do, hopefully, fingers crossed, I continue to do this research throughout the summer, so I have a little bit more time to continue to hone it and do more. I already have a lot of a lot of things that I want to do to continue to advance the levels of this research, and that's just one other thing that I could do to improve the rigor of it, so thanks for that. Sir?
So specifically looking at the Russo-Ukrainian, and you're talking about the drones, those are 100% driven by a human actor, not automated AI, something like that?
So the Ukrainian drones that are used, we're looking at both human actors that are operating it from kind of an alternative location or those kind of autonomous drones. So the data collection stopped at December 31st, 2025. I believe that down the line, if this research is continued and we start to pull data from 2026, and then if this conflict continues going on further years, we'll see more and more autonomous-based attacks as the technology improves. So moving forward within this research, it would be interesting to see when they're controlled by an operator, the success rates, and when they're autonomous, the success rates. And one thing I do want to say about that is that there's a pretty good amount of qualitative evidence available out there from scholars and analysts which indicate that relating to the skill finding, when the drone operator within Ukraine does not have much training, not much experience, not a lot of skill, the success rates, I don't know a number off the top of my head, If you want to know the number, you can come find me. But the success rate's it's somewhat low. But then when they have a lot of skill, when they've been doing it for years, when their experience is really high, it improves. And then when it's an autonomous system, it improves even further. So it would be, I think it would be really cool to look at that in a more vigorous way and collect data on that and see if that's true or not. So. Sir? I think that for the U.S. involvement within the China-Taiwan conflict, or a potential China-Taiwan conflict, I think the key focus for our drone operator training should be within the U.S. Navy. I think we're going to be sending our fleet over, sending our ships over, and I think that our sailors should be ready and trained well enough to launch and be able to conduct attacks against the Chinese forces from ships that are operational. So that attacking piece is very important. But we also can't forget the defensive piece. And when we're targeted, we need to continue to put resources and time forward to understanding situations like this, where we're looking into what makes different forces like the Ukrainians or the Russians successful in their drone attacks. And then we can have that framework to then learn what makes the Chinese drone forces successful in their attacks, so that when ultimately, if this conflict were to happen and they attack our ships, we know how to best defend them. And then lastly, may go without saying, but we need to absolutely continue to invest in self-defense of our ships and different countermeasures that we can take against the drone forces, because it's so new to conflict. We just don't know exactly how we're going to react. I mean, we've seen it. I think I mentioned before the USS Carney and the different one-way attacks from the Houthis, but not a lot of our ships, not a lot of our sailors have seen these drone attacks. So the more we can prepare for that, the more money and resources and time we can invest, the better, in my opinion.
We're going to do a quick swap of speakers and help yourself to some treats at the front if you're interested.
Thank you. Yeah.
going to give us a few words before you leave us.
All right, so just want to start with a little introduction. I'm a in first class. I use Sharma as my advisor, Dr. Nate Chambers, and this is our Trident research, reading between the lines, machine learning approach.
A little more unusual than the normal Trident. This was inspired by and mentored and advised early on by Professor Alex Schenken, who unexpectedly and tragically left somewhere lost and passed away. Hard hit to the department, hard hit to Mr. Sharma, and we wanted to take a moment to just remember him, dedicated to him. And I just want to read on behalf of the computer science department some words that are shared with memory of Dr. Alex was a much beloved instructor who taught courses across the computer science and data science curriculum. He developed highly popular course on computational finance, directed independent research with students, mentored several capstones, and prepared our latest Trident scholars. He was instrumental in bringing guest speakers for midshipman lectures, including Nick Cerf, one of the fathers of the internet. He provided midshipmen exceptional opportunities to meet and interact with clearly people. Alex could be seen supporting midshipmen across the yard. He was a fixture at Navy hockey games, which I wasn't actually aware of. Contributed to and organized USNA's participation in UMD's Information Challenge. And he was a big supporter of workplace events. You actually see him here surrounded by students. He just loved going to all of these things, which was not a requirement of his position as a candidate. Alex was an amazing teacher, colleague, husband, father, and friend. His dedication to his students was only matched by the warmth and kindness that he brought to everyone he met. Alex was someone who would always be ready to listen and that kind of stuff. Sorry, I hope I don't bring this down for the chicken charm. He was a great guy. He stood for my class one time, and I told my students who was coming. I was like, I told them I'm going to be missing next time. They said, oh, who's coming? I said, Dr. Timchenko. And there were audible, yes, all right. That makes me wonder if I'm like nothing. He was a fabulous guy. Like I said, he was a visiting faculty, but you would never know it. Permanent fixture in the department. Reached out to police. He talked about how great data science was. He was just one of them. Eventually developed into
Yeah, so more on that note, I fell in love with data science because of Dr. Timchenko. I came into the major with no coding experience beforehand. I actually told my parents, I'm never going to code in my life. I don't want to go in computers, but somehow, some way, I ended up as a data science major, and I started to really fall in love with it because Dr. Timchenko kind of showed me how you can apply this to finance, and that was kind of an interest I had because I was convinced that I was going to go predict Wall Street, but didn't really work out, obviously. But I have just one really small story, or two really small stories I want to share about Dr. Timchenko. The first one was when we were preparing for our Trident proposal. I was in his office for a lot of late nights just kind of fine-tuning it, and Dr. Timchenko told me a little story when he used to be a researcher at Goldman Sachs, and he told me that when he was up late working with his colleagues on a research paper, there was a kind bar policy where whenever someone found a mistake in someone's paper, they would owe them a kind bar. And so Dr. Timchenko would read my paper, and then he'd find some really stupid mistake I'd make, and he'd say, it's a kind bar moment. And so I'm in a lot of kind bar debt to him right now. But as a way, before I have been preparing for my Trident presentations and my mid-year presentation, I always eat a kind bar sort of as a token to his memory. And so I just want to share that story. And then also, the last phone call I had with him was when I was detailing plebe summer, and I'd called him during a little bit of my downtown, trying to go do some research, get ahead of it. And he explained to me some really complex math thing on the phone, and I kept saying, I don't really understand this. And then he told me, like, hey, we'll figure this out in a few days. But a few days, unfortunately, never came, and I still have not figured out that math yet. But we took the research in a different direction. But yeah, I was just really sad that there was this math that I will figure out before I leave this place. I will figure out that math just for him. But yeah.
So not only not most likely where he probably would have been sitting right in front of it all. And before you jump in, you got the moment.
Dr. Kapenka would definitely say, well, let's get a move on here. Let's speed up. So it's my honor, on behalf of Dr. Kapenka, to introduce Midshipman Sharma. We'll be doing reading between the lines machine learning approach to financial analysis.
Humans have been fascinated with detecting deception in speech for centuries now, and we didn't really get a real foothold in it until 1921 when Augustus Larson, a police officer, created the first modern lie detector. And this basically, kind of like we see in the movies, uses your emotions and stress levels to determine whether or not you're lying. But obviously, as we all know, it doesn't really work too well. And we've started to look into an approach into human deception that instead of using your stress levels when you're giving a statement, we look at your word choice. And we kind of call that reading between the lines. And Dr. Imchenko and I, we were trying to find where we can find this abundance of text to go analyze. And that kind of takes us none other than a walk down chaotic Wall Street. Wall Street's full of data, and that's the really good thing about Wall Street. However, this data is probably the noisiest data you can find. And it's for a good reason. Companies, when they're saying words about their company, they know everything's going to be analyzed. And because of that, every word is chosen pretty carefully, and it creates this sort of noisy world of data for us, where stuff like this is being said, this, or even this. But what does all of it mean? And that's where our research tries to read between the lines. And so, a lot of analysts, they analyze this thing called quarterly earnings calls, where companies talk about the state of their company in the quarter to the investors and analysts. And there's a lot of different questions that analysts have been kind of toying with in research in this area. And they kind of go around, do executives talk about the future? Do they talk differently when we're in recessions or periods of GDP growth? And do different executives in different sectors talk differently? The question that Dr. Chambers and I try to answer, though, is, can we model earnings calls? And this brings us to the contributions of our research. What we do is we create a new algorithm that models earnings call language for SEC filings. And this model has prediction results that improve 25.5% relative over baseline guessing. And we use Naval large language model pipelines for earnings call processing and 10Q parsing. And lastly, we present empirical results on modeling language across different sectors and GDP growth periods. So what is the machine learning approach? So the way a basic machine learning algorithm works is you have data and you have labels. In this case, we have these pictures of cats, frogs, and dogs. And we have labels of a picture of a cat labeled as cat, picture of frog labeled as frog, picture of dog labeled as dog. And we train a model that starts making guesses, fine-tunes its model weights, and eventually able to predict, is a picture of a cat, or is a picture of a dog, a dog. And so how does this look like when we're working with text? Well, our data comes in the form of, text, and our labels come in the form of outcomes, which in our research we use up, flat, or down. Train a model on it, you test some text, and you get an up, flat, or down rating from there. Now we're working in finance, so our text is going to come from these earnings call transcripts, and our up, flat, down ratings are going to come from the financial reports that are the outcomes of said text. So let's dive into what the data is. Let's start with the earnings calls. We work with 433 large U.S. publicly traded companies spanning 62 quarters. And these earnings calls, speeches they have every quarter, have free-flowing spoken word. And that's important because they're speaking the same way I am to you, where, yes, they prepare remarks, but mistakes are made. It's not like they're reading off of a script. And they're transcribing the text that's roughly 5,000 to 10,000 words per transcript, and that creates a total of roughly 125 million words for our data set. Here's an example of just one, and I've made it literally the smallest font Google Slides would let me make it, and this is not even all of it. And when you do the math on that, it's like we're reading In Search of Lost Time twice every quarter, which is the longest book written by man, 1.2 million words. What's really important, though, is that analysts are convinced these earnings calls matter. There is meaning in the words that are said in these. Now let's move to the labels. They come in the form of the 10Q. They're filed every quarter with the SEC, and they're heavily regulated, sort of as like the snapshot of the health of a company. Just all the numbers you can think of that a company could report is over there. We get them from the SEC website, and what's really important is that there are numbers in these lines that show up in the 10Q, and they show up in the earnings calls. And we define these as key performance indicators. They show up in there, but which line is talking about which key performance indicator is the real question. And that brings us to our 10Q pipeline, where we process the 10Qs. So we're working with 24,994 10Qs, and these are pretty long documents, and they're spreadsheets. Dr. Chambers and I, we don't want to read through all of that, to be honest. And we're going to turn these into up, flat, or down labels. And we'll define what that means further down the pipeline. But this is kind of what it looks like. We start with this big, ugly spreadsheet that is pretty difficult to read. And believe it or not, when we source this data from the SEC website, it gets even messier. There are no spaces between any of the words, which makes it a little hard for even me to understand what they're trying to say. But there's a number associated with it too. So we have this long string of text and 90.8 billion, whatever that means. But let's keep moving with this one line. We use a max match greedy algorithm that splits this into words, sort of with, not perfectly, but it's good enough for a large language model to read it and know what you're trying to say. Think when you put a prompt into ChatGPT and you make a typo, ChatGPT knows what you're trying to say. But now we have spaces, and we know that this is trying to say revenue from contract with customer excluding assessed tax. From there, we use our direct search large language model extraction algorithm. This is kind of our novel large language model pipeline where we start with the direct search. We have a list of, let's say we're looking for total revenue. We have a list of common ways total revenue is referenced in these 10Qs. And we basically apply this list to a 10Q and we say, are any of these lines, these words verbatim? Obviously, revenue from contract with customer excluding assessed tax is not in this list. So we need to move on. And that's where we go to our large language model extraction, where we basically ask a large language model which line is talking about total revenue. And so large language model does its thing, and it finds which line best does it. And now we found that this is the total revenue line. But as we all know, large language models are not perfect, and so we have another sort of line of defense called the verification gate. And so now we have this sentence, and we take it to a large language model saying, does this line talk about total revenue? And it responds with a yes or no, and that's how we get, yes, this is the line that's talking about total revenue. And now we're doing this for going through hundreds of lines. And this is all just from one 10Q from one quarter. Just keeps on going. So, we turn that messy text into this summary of, for each key performance indicator, these are the numbers we get. It's just an example of the output. So, how effective is this? And that's where we move to our accuracy across all the different key performance indicators. So out of the 24,994 filings, this is the completeness we have. And so you can see for net total assets, net income, we do really well. 99.5% is really good completion. But debt payments, because companies have different accountants, there's just such a wide range of how the accountants talk about debt payments that even the large language model couldn't figure out which one was debt payments. And then dividends was pretty low, but that's because not every company pays a dividend. For example, Apple from 1997 to 2012, they didn't pay a dividend, so that just shows as null. But we were confident with this completion percentage to move on with our research. And now we're going to see, what does up, flat, or down mean? So let's go take company A, random company, and investigate their total revenue across 3 quarters. $6,000, $10,000, $12,000. Look at one of these quarters and ignore the others. You can't tell a story of what does that number mean. And so that's why we standardize based on a mean. We define a mean, which in this case we took the mean of all 3 of these numbers, and we get a z-score based off of that. And so now if you look at one of these numbers, negative 1.07, that was a bad quarter. It was more than a standard deviation away from its mean. And so now we can see a little bit more of a story of what these numbers mean. And from there, we just bucket it into an up, flat, or down rating, where it's down if it's below minus 0.44 standard deviations, and it's up if it's above 0.44 standard deviations. And if it's in between the two, it's flat. But there are a lot of different ways to define the mean, and these are the 8 different ways that we found to define the mean. And what's really important to note is these up, flat, down ratings are completely different for each different method that we found. And so it kind of begs the question, which one is the way that correlates best to the earnings calls? And that takes us to the earnings calls pipeline. Let's take these 2 sentences we have from an earnings call. We're going to put it through a text encoder. And what this text encoder does is it turns these sentences, these words, into a vector representation of it. And this vector has meaning. Vectors that are close in distance are similar sentences, and vectors that are far in distance are not similar sentences. So there's a lot of meaning in these vectors. Think of it as like a way to code it as numbers. And so we get these vectors, let's say, from these sentences. Super long vectors, but let's take these vectors and we'll compare it to the definition of a key performance indicator. Let's do total revenue again. Total income from sales before any expenses are deducted. We're going to go turn that also into a vector using the text encoder. And we're going to take the cosine similarity between the 2 sentences that we found and our key performance indicator definition. And the closer one, that's the one that's a match. That's the sentence that we define as talking about total revenue. Let's go apply this to an entire transcript now. And these transcripts, this one is Apple's 2018 quarter 4 transcript, 8,200 words, 500 sentences, far too long for any of us to be reading. And let's see what sentences it pulls out. We have 1, 2, and 3. These are the sentences that the model found, the sentence chunks that it found as these are the total revenue sentences. But are these text encoders accurate? And so Dr. Chambers and I went through, we hand graded from 10 transcripts, we grabbed all the sentences, 240 sentences, and we went through all of them and say, our was human graded, figured out which ones were correct and which ones weren't. And these were accuracies. Now, as you can see, for some of these key performance indicators like total revenue and dividends, we were really good. Current assets, pretty bad. And to be honest, the 57% accuracy we had overall, we were pretty comfortable to move on. But what we decided to do was create another verification gate to make sure that the sentences we were pulling were pretty decent. And the way that this works is, take one of the sentences we found in that 2018 quarter 4 transcript. We're going to put it once again through a large language model verification gate where we're asking, is this sentence talking about total revenue? And the large language model will return a yes or no. And in this case, it's going to be a yes. So now we've gone through and processed through our earnings calls, and we've processed through our 10 Qs. So now we're on to modeling these earnings calls. As a little refresher of where we are right now in our machine learning pipeline, we have the earnings call sentences as our data, and we have 10 Qs to serve as our up, flat, or down. But we haven't yet defined what our mean is for these up, flat, down ratings. But we can move on with model training and kind of experiment with how we're going to move forward. And so we start with a neural network, where our input is those vector representations of sentences, and the output is a probability of up, flat, or down. And unfortunately, our accuracies were abysmal. The green and purple are the bars that we have for when we use those embeddings, and they're all negative, just across the board, horrible. And Dr. Chambers and I had to regroup. We're like, well, what's the problem? We did a deeper investigation into these text encoders, and we took these 3 sentences. This one is straight out of our data set, and we took this sentence that is the same as the previous one, but we just switched the word down with up, and then we just created this sentence for fun to see how it would go against the others. Just a random sentence. When we compared these 2 sentences, we expected it to be very different, and we calculated a cosine similarity, where if a number closer to 0 means they're opposite sentences, and a number close to 1 means they're identical. And this was the result. It was pretty different. The encoder knows that these are 2 different sentences. That's good. Now we compare these 2. And we were hoping for, maybe somewhere around like 0.6. So it knows they're similar-ish, talking about the same thing, but they're different because they're saying 2 opposite things. But the model thought they were pretty much the same. And that was the culprit. The encoder couldn't figure out the difference between down and up. And so now we go back to the drawing board and figure out a new way to encode these sentences for the model. And that's where we come to the word count vector. So let's take this sentence. The way that this would be encoded in a word count vector, pretty simple. You have the word, and the count is in that sentence. If it shows up once, it gets a 1, twice, 2, 3 times 3. If it doesn't show up, it gets a 0. And so when we use the word count vector, we actually saw those green and red lines are the ones that they were way better than the neural network or the embeddings, but they still aren't too good. And this is kind of just our grid search where we're finding out what we're going to go fine-tune on and make way better. And so our model summary, we know that we have word count vectors instead of those embeddings, those text encoders. And we're going to use a multilayer neural network instead of any other sort of model types. But we still know what our up, flat, down definition is going to be, and we don't know what our quarter shift is going to be. And let me talk a little bit about what quarter shift is. Let's say I'm talking about my watermelon cart company, and I'm saying I'm going to invest $200,000 in the future in a watermelon farm. You don't know if I'm talking about, am I investing that money now, 4 quarters in the future, or if I already put that investment a year ago and I'm just talking about it now. And that's kind of what we want to figure out. What quarter are companies talking about? But let's go to our up, flat, down definitions. Each one of these shows a different way to define up, flat, down, and we found that the 2 on the end had the best accuracy over the baseline, and that's kind of what we want to work with. We're going to go make these models the best. And so lifetime and Windows percent change, those are the 2 models that we're going to work with. Now what about quarter shift? Well, this is the quarter shift analysis that we have for those 2. And as you can see, lifetime has this sort of steady growth, and we investigated why. And lifetime has the mean set as the historical mean. Start with downs, go to flats, go to ups, because, well, that's natural growth of the market. Your revenue is going to naturally go up if you're one of the 433 biggest companies in the U.S. And so we decided there's not really any meaning in those predictions. However, Windows percent change was the only other standardization that had meaning in it. And so we decided to run away with that. That's the one we're going to use. Here's another perspective of it, where we're trying to figure out which specific quarter shift we're going to use. And the right is Windows percent change. And as you can see, there's no clear quarter that is the best quarter. And so intuitively, we just decided to stick with a quarter shift of 0 for the duration of our research. And so now we have our model. We're going to use a word count vector with a multi-layer neural network with Windows percent change as our up, flat, down definition and a quarter shift of 0. And this model, once we fine-tuned it, believe it or not, had a 25.5% increase in relative accuracy over baseline guessing, which is pretty significant. And we want to apply this to an economic analysis, and a sector analysis now. Here we're trying to answer, is our model more, or is language more predictive in good economic times versus bad economic times? And what we found is there's actually no correlation. Our model, the way the model reads it is, our model sees text in good times and bad times as the same. Similarly, when we did a sector analysis, we split up all of our companies into cyclical and defensive companies, where cyclical companies, colored in red, are the companies that follow those economic cycles. They are more prone to economic shock. Think like NVIDIA, Apple, those companies you always see in the headlines. On the other hand, we have defensive companies colored in green. Those are the companies that always have business. They don't really follow economic cycles, and they have a lot more defense against economic shocks. Then we have the unknown companies, which are the companies that actually fell out of the S&P 500 and they weren't in our data set of sectors. We expected to see, the red companies sort of have lower predictiveness because, they have to deal with more economic shocks and there's more uncertainty in their words. But as you can see, there's no real pattern in this either. And so our model sees that the text is the same between all the different sectors, which is pretty interesting. So let's move to the conclusion. Our contributions, once again, we have this new algorithm that models earnings call language for SEC filings. And it's pretty good at it too. 25.5% increase over the baseline guessing. That's pretty good. We have novel LLM pipelines for earnings call processing and 10Q parsing. And lastly, we do show empirical results for modeling language across the different sectors and GDP growth periods. And now future work that we have for this. First is to have end-to-end training for the encoder and the model. Basically that problem we had with the text encoder where it wasn't able to see the difference between down and up. If we use end-to-end training, we can sort of train that model to get better at that and then be able to identify that difference. We also thought about making the quarter shift span wider. Instead of just looking 4 quarters behind, 4 quarters ahead, and everything in between, maybe doing 8 quarters instead. Also try more complex neural networks. I don't want to say it's the fix-all, but it does fix a lot of problems. Also testing on the Federal Open Market Committee meeting minutes. These meeting minutes, whatever they say is usually what happens. So if the model is able to predict that well, it means that the model is working. And then lastly, we want to experiment with state-of-the-art large language models. So we're just keeping up with the times on that one. I want to thank you all for your time today, and I'll open the floor to any questions. Yes, ma'am.
Excellent work. I learned a lot. It was awesome. How did you arrive at the 0.44 standard deviation to define, level exam?
Yeah, so under a normal distribution, the 0.44 bands would split it roughly into a third per each category, each label. So that was kind of like the naive approach where we wanted to start with 1/3, 1/3, 1/3. And that's definitely something to tune in the future, I think. But there were so many different things we were tuning. We're like, we'll tune this one way later, and then later came, and we're like, we're just going to keep it the way it is. But yeah, I think that definitely could use some tuning. Yes?
Hey, great presentation. So how did you train these neural networks? Did it take a long time to train?
Yeah, so the way we trained them was really just putting in that input text with the labels. We had those labels up, flat, down with an 80% training split, 20% test, and we just tested based off of that. It did take a long time to train. It was actually a huge bottleneck for me because I'd start this program and I'd be like, well, what do I do for the next 2 hours? But yeah, it's obviously super computationally expensive when you're working with 24,000. I think we had like 300,000 pairs of sentences in up, flat, down that we're training in the model. So yeah, definitely computationally expensive.
Is it all on your laptop?
No, it was not on my laptop. Hopper Hall had the resources for that and it made it definitely way faster. Yep. Sir?
So how did you do, great presentation, thank you very much. Good stuff. How did you do the model selection? What did you try and nail down
Are you talking about the architecture of the neural network? Or yes. Yeah, so I took more of a naive approach where I just created a huge grid search for different parameters I want to change. So those parameters were neurons per layer. And I started with only 3 hidden layers, and I kind of just stuck with that as like, hey, this is what I'm going to do, which probably is not the best approach. But I tried different layers of numbers of neurons per layer, batch size, learning rate, and dropout rate. And so it was a grid search, and the one that was the best out of that grid search, after running a few iterations, there was a clear winner. That was the one that we chose. Yes, sir. Yeah. All right, so this is not a lie detector. I know the introduction made it seem like that, but I had to get your guys' attention. Yeah, a little bit of deception, you could say, yeah. But but what this does tell you is, hey, you're saying these words. This is what is going to happen when you say these words. So we have an outcome that we predict, and if it doesn't follow that outcome, then hey, this is deception, you could say. But there is the overall accuracy of our models were 55%ish, which is a little over halfway. But with finance data, that's a very, very good accuracy percentage. And that gap that we have between 55 and 100% really just comes from noisy data, which we can kind of sift through with a more complex network and better end-to-end training, or just the speech patterns they're just lying.
Isn't it possible that some amount of that 45% comes down to people who made misleading statements?
Yes, and that's what it is. So let's say whenever I say we are going to invest $100 million in capital expenditures, every time I say that, we end up taking money away from capital expenditures. We don't invest money in capital expenditures. That's what the model is going to learn. And so now the model is going to say, whenever I say I'm going to invest $100 million in capital expenditures, it's going to predict you are actually not going to do that. So it's basically, how predictive are you? Are your words?
So can you do a study then sort of like across time of a specific company, and if you're consistently wrong about that company, then maybe it means they're consistently misleading, right?
Yes.
Maybe if it's consistently right, then they're consistently truthful, or maybe your model will be better.
Yes, and that's actually Dr. Timchenko actually told me, like, what he wants this research to turn into is sort of each CEO talks differently about their company. And so you can kind of create a profile for each CEO and say, this guy has I don't want to call it a deception score, but has a score of, let's say, 0.4 or 0.3. What he's saying is just don't listen to it. Or this guy has a score of 0.99. Everything he says is going to happen. Yeah. Any other questions? Thank you, ma'am.
know if that's gonna download in the PowerPoint as well. Yeah, so this would have been the video. I don't know if it's Thank you very much, Professor Schroeder. As she said, I'm Midshipman First Class Molly Shosensky, and today I'll be sharing my research on the system identification and model validation of a blown wing tail sitter UAV. Before I begin, I would just like to thank everyone who's helped and supported me along the way and made this project possible. First, my advisor, Professor Andre Uhas, as well as two of our engineering technicians, Steve Galindo, who helped with the model building and was our pilot for all of our flight testing, as well as Dan Rogerson, who helped with all of our wind tunnel testing. I'd also like to thank Dr. Redinger, who is our external collaborator and is giving us a very relevant aerospace application for our results. And thank you to all of you for being here today. To start off, I just want to give a brief overview background of the relevance of this project and where it fits into the aerospace design industry as a whole. So UAVs, they are a hot topic nowadays. I'm sure you've heard a lot about them in the news. They're rapidly growing both in the commercial and military environments, and this is for a variety of reasons. They're really easy to manufacture, they're low cost, attritable, and they can be outfitted for a variety of different missions. In particular, there's a rise in UAVs with vertical takeoff and landing, or VTOL capabilities, particularly in the military realm. This is because of the ease of operation that comes with them, because they can be launched from anywhere, whether it's forward operating base or a Navy vessel, because they don't require a runway distance for takeoff and landing, so that makes them super relevant. As I said, with the growth in UAV and the variety of missions they support, there's constantly development on new configurations and new modes to optimize performance. One of these relevant configurations is the blown wing tail sitter. This is a relatively novel configuration, which means there's not a lot of flight test data rapidly or readily available for it, but it is super prevalent. On the left, this is a computer-rendered image of a UAV currently being developed by DARPA and Sikorsky, which is a Lockheed Martin company. As of May 2024, they had begun the preliminary stages of design and development, which shows the relevance of this configuration. And on the right, that's my UAV. That's what we used in this project. So what blown wing refers to is the positioning of the propellers and the motors in front of the wing, which means the wing will be subject to propeller wash for the duration of flight in both hover and forward flight. And then the term tail sitter refers to its launching configuration. So it launches with the nose pointed vertically, and then it pitches forward 90 degrees before it transitions to forward flight. This is super relevant because it allows us, and beneficial, because it allows us to maximize hover performance while also still having the benefits of a forward flying aircraft to include range, endurance, and speed. Now, the foundation of this project is system identification. That's a method of obtaining accurate dynamic models of aircraft from the measured responses to specific control inputs, so it models the aircraft's in-flight responses to control variations. That's a lot of technical words right there. What does this really mean? Well, I'm sure most, if not all of you, have been in an airplane before, and you've probably looked out the window and wondered, how in the world is this thing flying? Is it magic? Well, it's not magic, it's math. There are mathematical equations of motion that describe the aircraft behavior in flight, and we can obtain actual numerical values for those equations through flight test data via system identification. Once we have those equations, we can apply them to different mathematical modeling and simulation softwares to aid in the aircraft design process and make it more effective. And that was the main purpose and goals of this project. So we wanted to complete the flight testing of the UAV in both hover and forward flight, and from that obtain non-parametric and parametric system identification. Once we had those results, they would provide data to validate various modeling softwares, both capabilities we use at USNA, such as our wind tunnel and OpenVSP, as well as Stadium, which is a mathematical simulation modeling currently being developed at the Army Research Laboratory. Before we got into full-scale flight testing, we did some preliminary work, which was component testing in simulations in the wind tunnel and OpenVSP to obtain some baseline results. We started out with testing a half-span model in the closed-circuit wind tunnel right here in Rickunder. As you see, we cut the wingspan in half, and then we manufactured a test mount to interface between the wing and the force balance in the wind tunnel so that we could obtain the measurements for aerodynamic forces and moments. For testing conditions, we tested at 5 different aileron deflection angles over 3 RPM settings. And we did this to mimic hover conditions, which means we didn't actually turn the tunnel on with the freeze stream. We just turned on the propeller to get the motor response. Similarly, we also did a simulation in OpenVSP. OpenVSP is an open source parametric modeling software developed by NASA that allows you to make three-dimensional geometric models of your aircraft, and then it has a variety of built-in flow solvers and engineering analysis tools. So we built our model, as you can see on the left, with its geometric mesh, and then we simulated forward flight using its built-in flow solver VSP Aero. Once again, we tested at 5 degrees, or 5 increments of aileron deflections, and 3 RPM settings. Something to note is that the RPM settings for forward flight were lower than what we tested in hover. This is because forward flight requires a lower RPM for the motor because of the free stream over the wing that's generating lift, so it's less work that the propeller has to do. Here are results for those. We graphed the responses for lift and pitching moment and its variations with aileron deflection at the RPM setting. These validated our predictions about model behavior. As you can see, as the aileron deflection becomes more positive, lift increases, and it's also correlated with a negative pitching moment. In addition, the differences in the values for lift and pitching as the aileron deflection change, or the slopes of these curves, can be used to capture the control derivatives. These give us the aerodynamic component of those control derivatives, and that can be used to help out with model simulations. Next, we moved into our actual full-scale flight testing. So this was done in 2 primary locations. We did indoor flight testing for hover, which was in the Artemis lab in the basement of Hopper Hall, and then for outdoor flight testing, we were on Hospital Point. How we conducted our flight testing was through something called a frequency sweep. So we wanted to record the aircraft response to sinusoidal input signals. So we had an audio track that would tell our pilot how fast to vary the control inputs. And we did that for the 3 principal control axes, which was pitch, roll, and yaw. So pitch is the up and down motion of the aircraft, roll is side to side, and then yaw is the lateral. And then we recorded all our data using ArduPilot. ArduPilot is a commercially available autopilot software, and it has a variety of onboard logging capabilities. So we recorded our data through a combination of the inertial measurement unit, the GPS, and the accelerometer. This video here is an example of one of the frequency tests that we conducted. This was one of our indoor hover pitch sweeps. As you see, the aircraft is responding to the symmetric aileron deflection. That was the control input for pitch in both hover and forward flight. And then in hover, roll was controlled by differential thrust of the motors, and yaw was from asymmetric aileron deflection. And then in forward flight, that's swap. So roll was controlled by asymmetric aileron deflection, and then yaw was controlled by differential thrust. Once we had our flight test data, we had to reduce it. The main software we use for our data reduction is Cypher. Cypher is an aerospace software designed specifically for the purpose of system identification, and it has a multitude of built-in functions that carry out the different computations and parameters needed to complete system identification. And while Cypher has its own GUI, it can be interfaced with a variety of different aerospace tools, such as MATLAB, which is a very common, very widely used engineering coding platform. And so that's what we used for this project, is we accessed the Cypher database through MATLAB. The first step with our data reduction was from the full flight logs of our flight test data, we had to isolate the time histories of just the frequency sweeps. So ArduPilot records everything that happens in the flight, but we only cared about what happened when we were running our specific frequency sweep. So not the landing, not the takeoff, not the turning, just the frequency sweeps. So the first step was we had MATLAB code that would load in all the data and allow us to isolate that. From there, we used Cypher's FRESP-ID function to obtain the frequency response. So what this did was it used chirp-z transforms to translate our data from the time domain to the frequency domain. Chirp-z transforms operate similar to Fourier transforms, except you can specify the bandwidth of interest. Once we had that frequency response, we were able to fit a state space model for the equations of motion to the response using deriv-ID, and this was done through an iterative optimization process. So I know that was a lot of words, and so this figure kind of visualizes the process from beginning to end. So we start here, this is the time histories from our raw flight test data, As you can see, the frequency of the pilot inputs is increasing. From there, we use FRESP-ID to transform that from the time domain to the frequency domain, and that's outputted in this plot, which is known as a Bode plot. And these are the frequency response is this red and blue line on the Bode plot. So we have charts for the magnitude and phase of the response. And then here at the bottom, this is coherence. That basically is telling us how good is our data. Coherence is a measure of linearity from the inputs and outputs of the system, and so it tells us how much we have to account for variations or noise or anything that's impacting the results that's not to do with the control inputs. Once we have the frequency response, then we fit our equations of motion. This is the simplified state space model, so we have our input matrices, output matrices, state matrices, and parameter matrices. And what happens is Deriv-ID runs an iterative optimization algorithm that populates parameters for those parameter matrices to try and get a model that as close as possible fits the flight test frequency response that we obtained. So that was our process for how we conducted this research. We obtained results on the principal axes for both hover and forward flight. So that's the lateral, longitudinal, and directional axes in both cases. However, in the interest of time, we're only going to discuss the longitudinal results in this presentation. So starting off, these are the models we had to fit, the state space equations of motion for hover and forward flight. Our hover response had 2 degrees of freedom, and they were dictated by the pitch, rate, and attitude data, as well as the translational acceleration data. And then in forward flight, we only identified the short period motion, which occurs at high frequencies, and that was dictated by the vertical acceleration and the pitch rate. For both of these cases, the only control input we cared about was the longitudinal input, which was that symmetric elevon deflection to generate pitch motion. For our hover response, these are our results. The solid black line represents the frequency response, so that's purely from our flight test data, and then the dashed line is our state space model for it. The behavior we saw in hover is what's known as a hovering cubic mode, so that's a high frequency mode, and it means that the system is going to dampen out. We can tell this based off the combination of oscillatory motion and a first order exponential decay that can be seen in this graph by the peak, and then it decays out. As I said, we also obtained numerical values for all of the stability derivatives that were in the parameter matrices of the state space model. And I would like to draw your attention first to this value, MQ. That is our pitch damping derivative. And so because it has a high magnitude and is a negative number, that tells us that our system is well damped in pitch and hover. Additionally, I just want to address what Kramer route and insensitivity are. These are metrics for the accuracy of our model. This tells us how good our model is. So Kramer route is a measure of confidence in our parameter, and then insensitivity tells us how much each parameter influenced the cost function, which is the error between our model and the frequency response data. For both of those values, a lower number is better. The standard convention is a Kramer route under 20% and an insensitivity under 10%. And while you can have accurate models with values above those limits, it is something you would want to consider then when you're analyzing your results. It's also beneficial to plot the poles of the system to see their frequency and damping and how that informs the mode. So on this left-hand plane, this is our stable mode. This is the Fugode mode, which is a low-frequency oscillatory mode. We know it's oscillatory because it has a conjugate component, which is it's a y-axis value. And then on the right-hand side of this plane, this mode over here, that's our unstable mode, right? Because the frequency is positive, it means it's unstable. And that's very common. Almost all rotorcraft are inherently unstable in hover, and so that's why you need an active control system to counteract that in flight. Moving on to forward flight responses, as I said, we only identified the short period mode, which occurs at high frequency. We didn't have enough low frequency data to identify the Fugode mode. So as you can see, there's a peak at high frequency and then it begins to slowly damping out. Another thing I want to point out is the coherence, which is again a measure of how good our data is based on the linearity, is much higher in forward flight than it was in hover. This is very standard across flight test data just because there's less internal noise and vibrations in forward flight than in hover because the motor is operating at a lower RPM, and also the flight mode overall is more stable. So we expected to see that. Moving on, again, we have our numerical values for each stability and control derivative of interest. Most importantly, our pitch damping derivative, again, is a high negative number, which means it's well damped. And then this MW is our pitch stability derivative, and that value indicates that we have static stability. So that means if you aggravate the motion, it'll eventually return to equilibrium. Based on that, we expect our poles to be stable, which is what we see here. They're both on the left-hand side, and they're oscillatory, and there's no unstable mode in forward flight, which means it's stable across the flight regime. So from our results, we succeeded in obtaining an accurate parametric system identification model, which means we can trust our estimates for the stability and control derivatives. We also gained a little more insight into the flight behavior of the UAV. We saw that the hover response has a stable second order and unstable first order mode, and then we also saw that it was stable and well damped in the short period for forward flight. Another thing we discovered that was quite interesting is that our state space results closely mirrored the results for other aircraft that were done through system identification, in particular the Shadow UAV and the XV-15. And this was interesting to us because those aircraft are more conventional in shape. They have a fuselage, a vertical tail, and empennage, whereas ours is what's known as a flying wing configuration, so it's just the wing and the control surfaces. However, they had similar flight dynamics. This speaks to the merit of our design and why it's so relevant in the aerospace industry is because it's a lot simpler and it's a less complex model, but it has the same reliable flight dynamics as other full-scale aircraft. The purpose behind this project, again, we did the heavy lifting of data reduction and getting the data, but the main end goal of it is to be able to validate and apply it to different simulation models. The primary one we're looking to validate is the Stadium model. So this is a configuration agnostic modeling capability that's intended for advanced control system design, not necessarily flight dynamics, but it needs accurate flight dynamics data so that they could accurately predict how the aircraft will respond to certain control inputs. And that's what we'll provide. So our system identification results will allow a comparison metric for the trim and linear responses. Additionally, our OpenVSP and wind tunnel data provide insights that can be used for aerospace lookup tables to provide data on the impact of RPM on aileron deflection and the relationship between motor interference and wing deflection. Additionally, as I mentioned before, we could also cross-validate common modeling tools used in the aerospace department at USNA, including our wind tunnel and OpenVSP. As far as future work goes, our model that we have is accurate and it's a working model. However, it can always be improved. One of the primary ways we can improve it is by obtaining more low-frequency data. Again, we were mainly limited in the scope of our areas for flight testing as to how much low-frequency data we could obtain, and so we were unable to identify such as the phugoid mode in forward flight and other low-frequency modes. Additionally, we can test isolated parts of the UAV, so whether this is a wing in the wind tunnel or just a thrust stand, to isolate some of the control derivatives and time delays. And if we can fix those values in the parameter matrices in our state space model, that's less iteration that the software has to run, and so it can help make the other values more accurate as well if we fix those beforehand. Finally, we could also look into decoupling the responses of roll and yaw axes in hover and forward flight. So when the aircraft goes to roll or yaw, there's also a rolling or yaw response, an opposite response. However, because we have an active control system in our model, that automatically corrects for it, so that's not including in our flight data. That doesn't show up in the flight data because it's already accounted for on the front end. So, however, if we eliminated that and we decoupled those axes completely, we could get a more in-depth model of the true nature of the flight data. Because, again, while our model is good and it's accurate, the nature of engineering is that you can always be improving. So with that, thank you so much for listening, and I'm happy to take any questions. Yes, ma'am.
The first question I have, did you name your wing?
We called it the UHAS 2. So The base model came from a few years ago. The WRC department did a DARPA SORM project, and they were gifted all of these flying wing models, and they were known as a Zephyr model, so the Z. And so since this is the second iteration of the Zephyr model, and my advisor's name is Professor Juhas, we named it the Juhas too.
I love that. And then the other question I have is, are there design trade-offs in the geometry of the wing between like how it performs in hover and how it performs in forward flight?
Yes, absolutely. The biggest design trade-off that we noticed is just the planform area. So the area of the wing, we wanted the bigger wing and it's thinner just so it could generate more lift. So that's for forward flight. It increases speed, range, all of that stuff. However, in hover, when it's flying this way, it's perpendicular to the wind, and so it has a tendency with that pitching moment we talked about, it wants to constantly tip over. So that's why we found, because we flew it outside in January in Annapolis, and in really anything over 5 miles an hour of wind, it's almost completely unstable in hover. It can't vertically take off and land. We have to belly land it, because as it's coming down, you have to lower the RPM so that it will land, and you have to land it at a slight angle, and its tendency, because of the way the wind is hitting the wing, is it wants to either yaw this way or to completely pitch over. So that was the biggest trade-off we noticed. Whereas that's where you see like quadcopters or other VTOL UAVs that don't have a conventional wing surface and are more, they don't have that issue because there's less surface area for the wind to hit and for it to want to pitch or roll.
And you have to be able to post the sensors?
Yes. Oh, yes, ma'am. Yes, sir. Yes, sir. Yes, that is pretty much a totally different regime. So the system identification we did works when you isolate the two axes, so we didn't really model the transition flight, and actually the transition mode was done fully by the autopilot. So ArduPilot, which is that hardware interface we used, it has an onboard autopilot capability, and so what would happen is our pilot would launch it until it reached altitude for hover, and then he would switch it into the transition mode. It had 3 seconds where it would pitch down on its own, and then it would transition into fly-by-wire, and he can control it again. So that was fully done by the autopilot. But yes, it's very difficult to model, which is why it's not included in this research. Thank you. Thank you, ma'am. Thank you. Absolutely, ma'am. Yes.